Test. 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 Yep. Test. Mute.
Good morning. So, for the third and final ICFP keynote, I'm happy to introduce Katja Komandanskaya. She is a professor at Heriot-Watt University and Southampton. She studied at Moscow State University, did her PhD in University College Cork, and she has worked at INRIA and University of St. Andrews after that. Her research is about an interesting new programming paradigm called neurosymbolic computing, which combines artificial intelligence and neural networks with the more traditional, the more boring programming languages that many of us work on. In this third and final keynote, she will tell us more about this paradigm and also how you can verify programs written in it.
Thank you. It works? Okay. Well, thank you so much for inviting me, because I have good news to convey you. I'm so happy to be here and deliver those good news. Let me check that my controller works. It does. So welcome, robot. The robot's name is Isaac. You might wonder why I'm showing you the robot Isaac. Well, because it's a mascot of vehicle, and you might ask, and what is vehicle? Vehicle is a programming language. It's a Haskell DSL for writing specifications for neurosymbolic programs. You have a QR code there if you want to go and check out yourself. The important bit here, if you check out which languages are used in it, you will see Haskell as a majority of code. Then there's a bit of Cork, there's a bit of Agda in it. It will become very clear during my talk what's going on. Yeah, so the question is, okay, Isaac is mascot of vehicle, and what's vehicle? And why do you call it vehicle? And you might think it's because we're verifying lots of vehicles, old vehicles and new vehicles, but that is not the case. Vehicle is for verification condition language. And why it has to be verification condition language will become clear in a few moments. Since I'm showing you some vehicle and some people around the vehicle, there are two key people on this particular vehicle. This is Wen Koke and Matthew Duggett. They're the two main developers of vehicles, so I definitely wanted to see their faces here with me today. There are many more developers of vehicle than that. We are quite distributed. Matthew is in Australia, Wen Koke is in Glasgow. So this is only Southampton part of the group. Because I don't have a photo of everyone who develops a vehicle, I want to give a bit of credit to the other people who worked on this. So this is our recent FSCD system description of vehicle, and you have more names here to check out. And in particular, the person who needs mentioning and who wasn't on the picture with vehicle is Bob Atke, who contributed a lot to the design of this language. All credit is given. It's actually not vehicle specifically that I wanted to talk to you today. I will use vehicle as an example of what you can do with neurosymbolic programming, but not as our main target for the talk. So what is the main target for the talk then? As you have seen from the title, I'm interested to talk to you today about combining proof-carrying code ideas with neurosymbolic code and get something hybrid. Before I actually go into the details of this, I want to motivate a little bit why would I care about the building blocks in the first place. Well, let's start with neurosymbolic programs. The truth about them is that they're everywhere. And as an exercise for us all, since we need a morning warm-up, let's convert a standard symbolic program into a neurosymbolic program in 2 minutes. So what I'm going to start with is a classic example. It's a hello world example in verification of cyber-physical systems. It's due to Boyer, Green, and Moore. As you can see from the citation, if you can read it, it's from 1990. And of course, in 1990, it was purely symbolic. So here's the deal. The vehicle is moving on the x-axis, but Boyer and Moore were not interested in modeling the safety of its behavior on the x-axis. They were interested to model safety of its behavior on the y-axis, because the scenario is that the wind is blowing and trying to get the vehicle off the road. So when you see the red margins, these are the safety margins. We definitely want the vehicle to be within those y-axis, those red lines, between -3 and 3. What else to say? There's not just wind, the wind also changes. And how does the car deal with the changing wind? It has a controller. In 1990, just a standard controller, no neural nets whatsoever. That controller has access to 2 bits of information: the previous position of the vehicle and the current position on the vehicle on the y-axis. So of course, if you know your previous position on y-axis and your new position on y-axis, from there you can calculate quite a bit. You could calculate your velocity on y-axis, and ultimately this gives you some clue as to how big the wind speed is. All right. So why is it such a hello world example for cyber-physical systems? Because despite its being so small, it already has stochasticity because of the changing wind speed, and some uncertainty because already in 1990 example of Boy and Moore, they incorporated the possibility that the sensor is a little bit buggy, so it gives you potentially erroneous observations. So if I ask you, how do you convert this into a neurosymbolic program? Even if you're not a specialist in neural networks, you perhaps would have a few ideas. And the easiest one is to say, let's plug out the controller that was there in 1990s and plug in a neural network instead. So neural network will be analyzing previous position and current position and making decisions how to adjust the Y position of my vehicle. It's not only just possible to do this, everyone does it anyway, right? So we're starting with the premise that this kind of plugging out of old symbolic code and plugging in of neural networks is happening all the time. And there may be different reasons for this. Maybe my neural network could be more smooth in behavior, maybe it could be more adaptive, less sensitive to noise, or sometimes those symbolic components are just too big to be run on small drones or other devices. All right, so to give us something to think about, let's take Boyer and Moore example and have it in Agda. Of course, Boyer and Moore were not programming in Agda. They were programming in ACL2. It was their own language that they designed for verification of hardware and other interesting things. But why not having it in Agda? It actually doesn't matter in which interactive theory improver you do it. All right, so the state of our system has wind speed, position, velocity, and sensor readings. Observations are wind shift and sensor error. And then you see the controller. For Boyer and Moore, the controller was fully observable, and for us, it's some black box. So we just give a type to it. By the way, we use rationals here, but if you were using, say, ROC with its pretty real numbers, you could also imagine real numbers there. All right. So then you define the state, next state rather, how you transition from one state to the other. And here, there are only 4 lines for us really to read. And they are actually what you expect, right? So for example, to calculate new wind speed, you need to know current wind speed and add wind shift to it. For new position, you need to know current position plus add velocity plus new wind speed. Remember, when you read this, we're always talking about y-axis, so all this velocity, positions, it's all only on y-axis. So it even has a little bit of a flavor of differential equations, which is very standard when you model dynamical systems, because when you start talking about the rate of change, you always have this flavor of your equations looking a little bit like differential equations. So really not that much to say about this piece of code, except for to emphasize that we have modified Boyer and Moore example in these 2 little places. So we plugged out the standard controller, plugged in the neural net, and therefore, in the computation of the new velocity, it is now controller that decides how to adjust my new position. But this is about it. And then you just fold your next state operation over a list of observations, and then you can compute as many next steps as you've given the observations in your list access. All right, so far so good. So what did Boyer and Moore actually do with it? Well, they have the main safety theorem. And the safety theorem says this: if the wind speed never shifts by more than 1 per unit time, and the sensor is never off by more than 0.25, then the car will never leave the road. it is an extremely sensible condition, right? So first of all, you definitely want to guarantee that the car will not leave the road. But on the other hand, you cannot guarantee it for any circumstances. Maybe there is a hurricane and your car is blown off completely. So of course, you have to put the margins and just say, well, it is for this sensor error and for this wind speed that I can give guarantees. And if something very bad happens, well, that's where my guarantees do not stretch. So that's very normal for cyber-physical systems. And that's what they did. And you can reformulate the theorem in Agda for sure, any other prover you like. Crucially, when you try to prove the main theorem by Boyer and Moore, you cannot follow all the steps that Boyer and Moore have taken in their inductive proof. Because now you plugged out some of their symbolic parts, so you need to give some guarantees about your neural network. And the guarantees for our neural network come in the form of this lemma, which we called controller safety property. Well, think of it, what you might want your neural network to behave like. It can be arbitrarily fancy and creative, you don't care, but certain things you do care about. In particular, you want to say this: if my sensor, and the neural network takes sensor of the position, is actually, the vehicle is now between -3 and 3, so we are kind of within the safety region. Plus, because the sensor is buggy, I'm allowing this to be 325 in both directions. It could be -325 or +325, because who knows, maybe sensor is buggy at this moment. So if it's within this safety region, so I'm still sensing somewhere within the road, so I'm somewhere still there, I want to make sure that the output of the neural network, which gives me adjustment to my position, doesn't get crazy. So you see here, the left side of implications exactly tells me that, you know, my sensing is within the safety boundaries that I have, and the output condition that the controller output plus 2 times x minus y should be less than 125. I don't have any good explanation for you. It's just how the differential equations work out to give you the safety property. We had to do a little bit of manual calculation in order to have the second part of implication, though the left-hand side is pretty obvious. So if we do have this lemma, suppose I assume this lemma holds, then Boyer and Moore example goes through in Agda, and Agda is happy, and we're happy. But the question is, of course, is how can we prove the lemma now? Because now the blame is on the lemma. And Agda cannot prove the lemma. This is all black box, so what do I do? And that is the question: how can we enable verification of such neurosymbolic programs? So I hope that I have persuaded you that it's a sensible question to ask. In a completely different world, in a completely different place, in Popl, 1997, there was something else going on. There's this paper, Proof Carrying Code, that says something completely different. So let's switch gears and think about something else. So the paper starts with this: high-level programming languages are designed and implemented with the assumption of a closed world. In practice, however, programs often have some components written in a different language. All right, and so what does the paper suggest? It suggests to massage down the problem into blocks. So you have a code consumer, that's your safe language. It's already trusted. And you have a code producer. It's a language that you don't trust. So your code producer, the one who you don't trust, produces a safety proof. And then it packages the safety proof into a verification condition and ships that to the language that you trust. And then that proof is validated there in the language that you trust. So that's the whole premise of the proof carrying code idea. In that paper, the actual example that was worked out was this. So the standard ML code was your code consumer, and your code producer that you didn't trust was assembly code. And then the proof search was implemented in ELF on the red side and validated in LF on the green side. Just to give you an idea that it was specifically not about neurosymbolic programs, it was about something else. And you see verification condition appears second time. So that's what gives name to a vehicle, to the vehicle, to our tool. And you could kind of smell already that something is going on. It almost looks like, oh, you know, you're just plugging together neurosymbolic programs and proof-carrying code, and I'm done. So for the rest of the talk, I'm actually going to concentrate on how you do it. And of course, I'm going to be based on how we did it in vehicle already. But I really invite you to think how you would do it, because it's not necessarily the only way to have neurosymbolic code in a proof-carrying mode. However, what I would like to say in my talk is that even if you do it differently, not in vehicle, not in our team, although you're very much invited to join us, you would probably have to deal with these 3 blocks. You will have to have some very good typed verification condition language in order to handle your different interfaces. And then you need to plug it with the ideas of self-certifying code and neural code synthesis. These blocks will become clear as I go, so the rest of my talk will just cover each of these 3 blocks in order. So my thesis is that if it was not us, if it would be you who does proof-carrying neurosymbolic code, one way or the other, you will have to rediscover those 3 blocks. So I'll try to persuade you that that is the case. So why would we need a good typed verification condition language? Let's look in the abstract. So let's look at neurosymbolic program abstractly. So you have S, that's your old symbolic program, and you plugged in this neural network inside. All right, and then you have a safety property. That's our big Boyer and Moore theorem as an example. So you have something in mind. You, of course, want to prove that this property holds of your symbolic program and the neural network inside. Usually, if you use machine learning in the first place, you're assuming that there is some hypothesis there to be discovered by the machine learning algorithm. So there is a hypothesis from problem space to result space. Think of this, I know if your autonomous car has a computer vision unit, you're assuming there is such a function that would allow someone to recognize any pedestrian in the world. Yeah. So you're assuming that in principle there is the function that could be approximated. Oh, an important thing to say is that problem space and result space of my hypothetical function are semantically rich. So it could concern velocity, angles, distances. In this case, the semantics is the physical behavior of the system. If it's a pedestrian, also we probably have some kind of notion of a pedestrian in our minds. So one way or the other, this hypothesis that I think exists has problem space and result space that's semantically rich. And then, of course, we want to approximate this using machine learning. So we massage that down further, and we implement embedding and unembedding function, because neural network will only operate on vectors of reals or floats, depending on your implementation. And usually floats by the time you actually implement it. So instead of problem space, now you have input space for your neural network, and instead of result space, you have output space for your neural network. And of course, what happened now is that input and output spaces are semantically meaningless. For example, if I had a semantic of a pedestrian, now this all got reduced to pixelated images 1,000 by 1,000, and that's it. So the semantics of a pedestrian is gone. It's just simply an image of certain size. If I had velocity and angles and distances, they potentially were all normalized between 0 and 1 or -1 and 1. And again, I lost any meaning for that. So that will be important for our verification efforts. And that's one of the big obstacles that we discovered when we just started this project. But one way or the other, once you have input vectors, output vectors as your types, you can train machine learning system F. And I'm using the colors here, red for unsafe, green safe, and orange is kind of a gluing layer between those two worlds. Right, so it turns out that what I actually want to prove is that my property holds of symbolic system and of combination of these functions, embedding and unembedding function, and the neural net. Well, Agda couldn't do this either, as you can imagine, and neither would ACL2. So I need to do something about this. How about this as an idea? I will isolate the two parts. And in fact, as far as we have seen my running example, we've already done it. I will first formulate this first property that for every h, if some property q holds of h, then it would guarantee for me that my property p, that is desirable property, holds of the symbolic program and this hypothesis h. And then I will leave an obligation to prove this q separately. That was my lemma that I shown you in my running example. So I'll show this lemma q. It should hold of the system and my neural network with embedded and embedding and embedding functions. Well, that's some progress. That's not too bad. But again, I don't have any tool that would allow me to prove the property double I. So what do? I need to do something further. So I split that even further. Luckily, I have tools that would be able to prove some property of a neural network taken in isolation. And then I just need a middle layer to show that if a neural network is proven to have certain property, then my property Q holds, and then I will be able to go back to my AGDA and ACL2 and finish the proof. Are we good with that? All right. So to wrap it up, the overall proof development for neurosymbolic program will consist of these parts. So I want to prove big property holds of everything. Then I need to find problem space property Q, my lemma, that would allow me to prove the big theorem I have. But then I also need to find input space property R that will hold of my neural network F, and then also prove that this input state property implies my middle layer property Q. So this is essentially what it boils down once you write this up. And our running example has already taken care of stages 1 and 2. So mainly I will concentrate on steps 3, 4, and 5 now. So let's start with neural verifiers. I'm not sure how many people know about neural network verification. So I'll give like a baby tutorial for you so that it makes sense. So a range of neural net verifiers exists. So there is VNN comp competition that is run during CAV every year. And if you're interested to see statistics, what those verifiers are like, please check the competition webpage. I'm just listing few that I know and like. Marabou is based on linear programming and SMT solving. Iran and Prima based on abstract interpretation. This second one, Iran and Prima, is often published in POPL. So if you ever go to POPL, check out. This team tends to be publishing there. VeriSeq based on interval arithmetic, alpha beta crown based on linear bound propagation. Point being that the actual nitty-gritty details of how they implement verification of neural nets differ, but they all somehow work in this manner. They carve out the subspaces of the input space. And then they see what happens with the subspace as you start processing it, taking it through the layers of a neural network. Then they check what happens on the output space, what kind of subspace of the output space gets covered by the time you get your input space shape through the neural net. And then you can make a conclusion whether you got yourself into safe or unsafe subspace of the output space. And the picture is due to Iran and Prima team. But I want to discuss with you a little bit how this is actually done, because I think it's interesting and it will be important for us later on. So I'll concentrate on reluplex algorithm that was introduced by Kai Katz and that underlies the Marabou verifier for neural networks. Reluplex algorithm is based on simplex decision procedure known in linear programming, and it specifically works for linear real arithmetic, because that's what you need for neural nets. So let's have a look at this example of a tiny neural network. You can see it there on the right. And I'm specifying some verification condition for it. I'm saying, well, how about this? Can you prove for me whether this is SAT or unsat? If inputs to these neural networks are between 0 and 1, I want to ensure that the output is between 4 and 5. Now, it's a slightly different example to what we saw in the Boyer and Moore. reformulation, but it has the same feeling, like I'm putting some boundaries on the inputs and I'm checking whether certain boundaries on the outputs hold. This is iconic for neural net verification. This is a sort of guarantees that neural net verifiers give you. All right, just a reminder for those who have never seen neural network or see neural net definition and forget it every time they see it. So there are a couple of very simple functions going on inside of the layers of neural networks. So first of all, given some signals, some inputs from x1 and x2, for v1 and v2, we compute the weighted sum of their inputs. So for example, the inner sum for v1 is 2x1 plus x2 because the weights are 2 and 1. And once you compute those inner sums, you also apply a ReLU function on top. ReLU function simply gives you 0 for all the negative inputs and gives you identity function for all the positive inputs. And that's really all there is if you wanted to define a neural net. All right. So the duplex algorithm goes in this way. It says, well, let's say we have a variable vector and put all those key components of a neural network as a variable. All right, so x1, x2, inner sums, results of inner sums of those. Then v1 and v2 are the results of applying ReLU to in1 and in2. Let's not worry about aux1 and 2. And then there is y for the output of the neural network. The bounds, initial bounds, are given to us by the verification condition that we have. So we may just ask how to propagate those bounds. So assuming in1 and in2 are the weighted sum, clearly that the fact that x and 1 are between 0 and 1 already determine for me the boundaries for in1 and in2, right? I simply propagate the weighted sums through it. So let's have a look, for example, how number 3 is computed. So 3 and 0 as lower and upper bounds. So that is in 1. So we look at v1. You can see that x1 and x2 maximum can be 1. So the maximum of their sum would be, bear in mind that their weights are 1 and 2, will be 1 plus 2, 3. So that gives me the upper bound for in 1. And what will be the minimum of their sum? Well, if x1 and x2 as their minimum are 0, then the minimum of their sum will be also 0. And you can imagine, you can keep on propagating. For example, next time I propagate the bounds, I apply ReLU. So ReLU does identity on positive inputs, and it converts -1 into 0. Because all the negative inputs, it converts to 0 by definition. And then you continue. OK, so then you have this variable vector, and you have your lower and upper bounds. And what you need to find out is whether it's in some sense consistent, because 5 and 4, I just put them by definition of my verification condition. I need to actually check that this gives me a consistent problem, right? Because who knows, maybe 5 and 4 were arbitrarily chosen. They are not obtained by propagation of the bound. OK, then the duplex algorithm proceeds by massaging down definitions of these neural networks, or rather functions of this network, into equations. For example, if you have a look at the first one, it says that 2x1 plus x2 minus in1 equals 0, where it's similar to saying that in1 equals 2x plus x2, and so on. So for every neuron in your neural network, you generate an equation. And then you may also wrap up these equations into a tableau, an array of numbers, but in formulation of the algorithm, it's always called tableau. So for example, the very first line, you could see the coefficients for x1, x2, and in as per the equation number 1. So there is a lot of nitty-gritty stuff going on there. This is all a preparation for applying a Farkas lemma in checking that this all makes sense. So the duplex algorithm will go and try to find an assignment for my variable vector x, such that that variable vector, that vector v, is between lower and upper bounds on the one hand, and then if you multiply, take a dot product between a and v, you get a 0. So if that happens, it means your v is a solution to the problem. If the algorithm fails to find such a v, it will report that there is no solution that exists. So this mode of computation is very similar to SMT solving, yeah, to any SAT-unsat problem. Either you find an assignment that satisfies certain condition, or you report that none exists. So the procedure is sound and complete. Okay, so this is just to give you a little bit of a flavor of what's going on. We did not implement Marabou. We only helped to eliminate some bugs in Marabou, but otherwise this already existed when we started to work on vehicle. Well, wonderful. That's great. The technology exists, we can use it, why not? So how about then embedding proofs? Suppose Marabou works for us and it gives us an output. How do we embed this back? And this is where vehicle comes into play. So vehicle is a specification language. You state neural network properties in vehicle. And the first thing that you want to do is to send it to Marabou to have this neural net verification. It is shown, the stuff that I've shown you, duplex algorithm and execution of it, is shown as a devil here. But really it's just as an algorithm as any other. It's simply that we cannot fully trust Marabou. It's quite a big implementation. But otherwise, why not? We run the Marabou. We get certain guarantee from Marabou that the property holds. We lift it back to the specification language and pass it back to Agda, Rock, Isabel, Hall, to whichever prover you want. Agda was the initial interface we implemented. Rock has been implemented this summer, and Isabel Hall work is underway. So that's the idea. Let's have a look how it works. So this is now vehicle, finally. So that is the Haskell DSL, so it looks a little bit like Haskell. So this is our middle layer between low-level crunching of vectors and arrays in Marabou and very high-order reasoning on the Boyer and Moore example, or in any example you want to program in your interactive theory improver. So let's have a look what vehicle does. It's a hopefully no-nonsense language, because we were hoping that actually practitioners who verify neurosymbolic programs will use it, not necessarily functional programmers. It has dependent types, but it doesn't have induction or recursion. So naturally, and this is a vehicle property for Boyer and Moore example, naturally it goes and specifies inputs and outputs of neural network. Remember, my neural network takes two inputs, previous and current position of my car, and gives one output, how to adjust my position, or rather my y velocity. So therefore input is given by tensor of reals of size 2, output is given by tensor of reals of size 1. The neural network here is not defined. It lives somewhere else in a different file, but we give its type. The type of the neural network, which is called controller here, is from input to output. If there is any normalization procedure that used to be hidden under the carpet before, we must declare it here. It's this embedding function that we were discussing. In this case, we don't use any unembedding function. It's only the embedding function that we declare. And then I define safe input and safe output, just as I told you 10, 15 minutes ago. So this is just vehicle's representation of boundaries on two inputs and on an output. And then the main controller safety property, that's the lemma that we have finished with our example with Boyer and Moore, says that you must guarantee for me that safe input guarantees safe output. Okay. And this is all. So this is all we need in order to specify this middle layer property for Boyer and Moore example. What do we do with it? Well, let's run vehicle. If you scan this QR code, you could get yourself to a tutorial. It's very easy to install both vehicle and Marabou. You just have a pip install command on the tutorial page. It's installed. You need to have VCL specification that we've just seen on the previous slide. And you need to have your neural network in ONNX format. It's a format that is used by neural net verification community to verify neural nets, so we just kept it there. Then you have a command line in your terminal, vehicle verify. You say which specification, it's the wind controller, which verifier Marabou, and you give a path to your neural network. And after just a very few seconds, vehicle will tell you that it's safe. It says, hey, Marabou has proven that there is no counterexample for this property. Hooray, you're done. Okay, so let's just stop and think what has just happened. Underneath this execution, at least two things happened. First, vehicle computed the property R, because we didn't give it a property of a neural network. We gave it a property of the lemma we want so that the more and more example goes through. So it actually computed this R for us, the suitable neural network property. And then it has proven that neural network property implies the orange, the middle layer property. So how did that happen? So first of all, let's have a look how it computed this R. As you can see there, it says verifying property safe, 2 out of 2 queries. And if you're like, okay, what are those queries? If you actually go down the files and see what vehicle generated, you will see that these are the 2 queries, and this is the format VNN lib that is used by neural network solvers. You may be from that community or from functional programming community, but I'm asking you, would you like to write properties of anything in a language like this? This is the whole file. It doesn't say what the types of X and Y's are, where they come from, what it is. No one knows. It's just this is the whole file of specification for a neural network property. Should any human write properties of neural networks in this way? I don't think any human being should. And before we implemented vehicle, that's how human beings were writing neural network verification properties in this language. It's a VNN lib standard. So it might be good for a compiler, but you certainly don't want to specify properties for systems in this language. So we have it hidden. Hopefully the user of vehicle would not see it. This is something that Marabou crunches once it starts working on this. All right. And how about proving that this strange Marabou property implies my lemma? Well, there is a type checking mechanism in vehicle. So first, after scoping, it does the type checking. It will normalize and generate the queries to Marabou, just as we've seen. There are other things that this type checker does. It will have for us checks for linearity errors and quantifier errors. Why is that? Because vehicle is high order language. It has dependent types. It's much richer than the language of VNN lib to which you compile. So it's very possible that you specified something in vehicle that Marabou cannot crunch for you. And this check will flag for you if you have specified a property that's outside of the fragment, decidable fragment of what Marabou can do. In particular, Marabou expects linear properties and a very specific quantifier nesting. All right, so thanks to the type checking, to the type system, we have the guarantee that that low-level property of neural network that I have guarantees for me the middle layer property of the system, and that is very nice. This is something that we really need. All right, so let's just wrap it up. Let's finish more and more example. We have just gotten proof of this lemma from Marabou, well, through this middle layer specification language. And how about finishing this? By another command line, vehicle generates for you an AGDA file automatically that is simply a translation of the specification that we've done in vehicle into AGDA. So this will be a separate AGDA file that you can use in the proof of your main theorem. It looks a little bit dirty, a little bit ugly, because it's automatically generated AGDA rather than human-written AGDA. But otherwise, this is the file that you're going to be using to finish off your main theorem. And so in this type checking system, you add yet another leg. You now compile this all to ITP code through another pass to your type checker. And as I said in the moment, we have AGDA rock and interfaces working, and Isabel Hall is going to be ready very soon. But point being is, once you have this bool set type check implemented, adding more and more interactive theory improvers is actually becoming a mere engineering task. It's not that difficult. You're still reusing the same typing procedure for all of them. So that's nice. So to sum up, what just happened? We have just noticed that in verification of neurosymbolic programs, we have an embedding gap between the problem space that is nice and safe and has our interactive theory improvers and our nice specification language. And then there is this embedding space that talks about vectors and kind of somewhat untrusted, at least notionally. And so we have just implemented a compilation procedure from specification language vehicle to the verification languages such as Marabou, and build the embedding gap, bridge the embedding gap. So that is as much as one needs to know about the vehicle. So it handles the embedding gap safely, builds SMT backend in the form of Marabou, and type system generates and handles complex constraints consistently. So that's all nice. I will very briefly tell you about two other quirks that happen in implementation of this language. And let's start once again with Nikula's idea. The thing is, when he was suggesting this in 1997, if we think about how this whole idea fails, and I'm having a table there calling symbolic PCC I'm using that word to refer to Nikula's example. The incidence of code that fails verification condition assumed to be low, right? Okay, he was saying assembly code is very unsafe, but he was assuming that basically there is a bug once in a while, but it's not like it's totally unsafe all the time. So first of all, the incidence of code that fails verification condition was low, but if it did happen, the assumption was that it was amenable to manual repair. So if an error in assembly code was found, then someone would be able to go and actually fix it. And what happens in neural network case, in neurosymbolic case, is that if we have our vehicle implemented and so on, and just run it, well, in some cases, up to 96% of cases come back to you and say, it's not verified, sorry, this specification that you've given is not valid for this neural network. And then what do? You cannot just go back and manually fix the neural net. So, of course, the idea is to somehow get to fix the neural network without doing it manually, because there is just, it's going to be your routine. If 96% of cases you fail, then fixing a neural network should become automatic for you. It cannot be done on an ad hoc basis. Well, thankfully, machine learning people have thought about this long ago. So it's a very popular topic in machine learning. You can optimize machine learning models for a property by generating new data, new loss functions, and some other parameters. I'm just last night looked up any new paper in 2025 that I like on this topic and provide it as a citation. But literally at any point you can go and check what's the new paper on property-driven training, and you'll find something. There's abundance of stuff in there. But the one that we picked up was based on generation of new loss functions. And I'll give you just a very quick example, because I don't want to give you anything in machine learning terminology. Suppose I have a toy language to write my verification conditions, and it only has comparisons between x and y's and a conjunction. Well, I can define a translation for each of my expressions in the language. And for example, I'm going to be saying that x1 is less than x2. I'm going to be interpreting as subtraction. Why is that? Because if x1 is actually smaller than x2, then the result of subtraction will give me a negative value. It means the penalty for a neural network will be negative, so there is no penalty. But if x1 is greater than x2, the value will be positive. It means the neural network will be penalized with the actual value. The penalty will be substantial. And then suppose I wrap conjunction as multiplication. And then you can use the resulting function as loss function to optimize the model. And to persuade you that it kind of works, I just put an example here that we used to show you how the duplex algorithm works. Remember the one when we had 0 and 1 boundaries for input and 4, 5 boundary for output? You could put it through this translation and can get some crazy function that is, again, pretty meaningless. And once again, probably you don't want a human being to write anything like this, because the meaning is somewhat lost. But you can use this yellow loss function in order to optimize your neural network to satisfy the property that you want. Luckily, I don't need to say much here because vehicle has already infrastructure to handle for us the dirty world of machine learning. So we get here a result for free, essentially. You see that there is some empty bit in the square. So of course, I'm going to fill it in, if I may. So if I can generate loss functions from specifications, and I can, I simply plug this in inside of my compiler. Since I have property Q written in vehicle, I may just say, please, vehicle, could you generate for me these loss functions, pass it over to this red world, do the training with this specification property R. If verification for R fails repeatedly, could you have this loop several times, train it until the property is actually satisfied? And actually, I don't want to see it in my green world. Just do it at your own leisure. The only thing I really care about is that my compiler handles compilation from specification language into a loss function, and the rest happens on its own. So that was for free. What wasn't for free? We spent quite a bit of time proving properties of these loss functions, because for machine learning people, it's not a problem. They could do whatever they liked. But if you actually want this to be part of your compiler, you probably want to prove something about these differentiable logics and loss functions. So we've proven some soundness properties and some properties that are pertaining to training, like smoothness and monotonic increasing for or decreasing properties for conjunctions, junctions. And so that was published in ITP last year. All right, so we have extended our picture somewhat. Now vehicle has 3 interfaces: to verification, training, and finally integration with the provers. So here you are. All that we needed to do is to have another type checking pass into differentiable type checking part of our system that will generate loss functions, and then TensorFlow will take care of the rest. So in neural code synthesis was almost trivial. So loss function synthesis via differentiable logics, that is fully done, and TensorFlow full program synthesis from vehicle is in progress. So we don't actually have this backend fully working yet in TensorFlow because it required quite a bit of engineering to do composition of all these loss functions if you have big specifications. But basically, it's engineering work rather than a rocket science at this stage. All right, and very quick note on self-certifying code. There is a third important building block. Going back to Nicola, in his case, he could actually, because his proofs produced by the code producer were written in ELF, and then he needed to validate them in LF. The gap between these two languages of the initial proof that was found by the unsafe side and the safe one was extremely small. It's quite easy to convert one proof into another. And in our case, Marabou proofs through reluplex are so different from the proofs you have in Agda. So we needed to think a little bit about this. Luckily, there is something that's called self-certifying code tradition. And if you've never heard of self-certifying code, I'm providing the citation to Communications of ACM this year, which has a very nice overview of different approaches to self-certifying code. But going back to the problem in question, verification of SMT solvers, forget about Marabou and neural network verifiers. Verification of SMT solvers is a no-go. They're too big. No one has ever verified a whole implementation of an SMT solver. And similar would be with Marabou. Not for a single moment we consider taking a Marabou and verifying it like in a comp-cert manner. But what is a nice solution for SMT solvers is to generate a trace of execution of an SMT solver. And then have it, you can actually even render it as a proof term in your interactive theorem prover. And this is a path that CVC5 has taken, and now it can actually render those proof terms into lean. So this has been done in SMT solving and interactive theorem proving community. Clearly, one could consider that the same thing could be done with Marabou and vehicle. So what's the deal? The team of Amri Isaac, Clark Barrett, and Guy Katz already thought about this, and they have published a paper in FMCAT 2022, where they basically conveyed this information. If you have a neural network, you have your specification, and you have your verifier, in their case, Marabou. Then if an instance, if this vector V is found, that's your counterexample, and you can immediately check it. So that's not a worry. The problem is that even you have a case unsat, the case unsat basically says, I couldn't find any example. Well, that was very difficult to certify. And their idea was that, well, we could produce these certificates during the execution of Marabou and then have an independent checker to check those certificates. How did they do this? Apparently, there is a Farkas lemma, very famous in computer algebra and linear programming, that gives you certain guarantees on SAT and unsat of linear programming problems. So if you have A, X, L, and U, as per my previous example, exactly one of the options holds. Either you're in the SAT case, so you could find a vector V that both is between your upper and lower bound and gives you dot product with A equals 0, or you're in unsat case. So SAT case we have considered in good detail within this talk. But there is also unsat case to the Farkas lemma that says that if it's unsat, there actually exists a contradiction vector, so that if you, for any x that is between your lower and upper bound, you multiply the contradiction vector by A and X, and when I say multiply, it's all dot products, then the result will be less than 0. So the Marabou team, of course, had this big idea. They said, why don't we have a constructive Farkas lemma for Marabou, and that will be our way to generate those certificates. So the contradiction vector W can actually be constructed during the execution of Marabou. The idea there, on top of the fact that you use Farkas lemma, is that Marabou has, and reluplex algorithm generally, gives rise to some sort of a tree structure because of processing of ReLU nodes. So it searches for LP assignment, either it's find contradiction, or then it starts going inside of the ReLU nodes, then starts checking piecewise linear constraints, which are ReLUs given by ReLUs, and then either it finds a counterexample or splits into subqueries and repeats. So if you were to visualize the whole proof search in Marabou, it will be like a big tree. For our tiny example, though, because there are only 2 ReLU nodes, there will be only 2 splits. And in particular, so for our example, this is how reluplex search would look like. It's a ReLU split on the node V2. The details are not so important here. The point being is when you finished the search, when your proof tree is there, in each leaf of that tree, you could have a contradiction vector computed during the execution of reluplex. So that was important for the Marabou team. And then if you do assemble those contradiction vectors at the leaves, you can just plug it inside the Farkas lemma and simply check whether these contradiction vectors satisfy the Farkas lemma, and you're done in terms of certificates for your unsat. Well, it's quite a mouthful. So obviously, when they presented this at FMCAT 2022, the obvious criticism to this, can we actually be sure that this is all correct? Because it's a little bit hacky. Something happens with vectors, contradiction vectors. If you wanted to put this inside of a compiler, you have a little bit of a job to actually prove that this all gives you something valid. Even the theory is nice. In terms of programming this stuff, it actually requires quite a bit of work. So in proof-carrying code, we need to formalize and prove the constructive Farkas lemma in entrusted theorem prover, and then use this formalization in independent certification of Marabou proof trees. So this took us quite a while. It was published in ITP this year. So finally, we have this certified proof checker, and it was implemented in Amandra because PhD studentship was funded by Amandra. But it could be done in another interactive theorem prover as easily. So to summarize, we have formalized constructive Farkas lemma for reluplex. and implemented independent certification checking. There is quite some work to be done on doing these proof certificates compositionally in vehicle and perhaps even generating safe neural networks from certificates. So it's not fully done, but a big chunk of work is done. So to conclude, proof-carrying neurosymbolic code broadly follows the principles of proof-carrying code. But there were 3 quirks, and I think anyone who would do this again or would be compelled to do this again is bound to rediscover these 3 things. So first of all, you need a very good verification condition language that will help you to bridge the embedding gap between neural and symbolic domains. And types are ideal to keep you right there because there are just so many backends and you want to have some source of truth. You would probably have to again rediscover synthesis and repair of neural components using quantitative logic, simply because not every time that you try to verify something, you'll actually be able to do it. And finally, you will need to sort out the question of self-certifying code, because it's not enough to just say Marabou has proven it and I don't want to see it. You probably want to leave those certificates back to your high-order language, so that's important. So the important message is on this slide, and it's like rejoice. Not only you can do it, but actually programming language and types technology of the day allowed us to do it almost for free. When we were with our team discussing whether to submit vehicle to ICFP or POPL, there was always opposition within the team to submit it to ICFP and POPL, because the argument was that it doesn't actually contribute anything new to programming language design, which for us may be a bad news. But it's wonderful news for programming languages. It means that in 2020, when we started this project, the technology with types, theory improvers, functional languages was so high that such a complex project could be achieved essentially at no additional theoretical cost. So this is a big news I wanted you to know about. It's a congratulations to this community for this. And I wanted to finish with just quick postscriptum. Because you would say, well, this is so cute, there's vehicle and robot Isaac, and everything has nice interfaces, but what's the catch? I mean, how real this whole thing is? So we probably need to discuss large and small language models. The catch is this. So the technology on which vehicle was relying and our proofs were relying was verification of neural networks. And really, neural net verification is proven to be NP complete. So this is bad news, of course. Still, nonetheless, and same with SMT solvers, some of them are NP complete, and yet people do improve their performance. Similar situation happened with neural net verifiers. Since 2017, neural net verifiers saw speed up to annual rate of about 1 order of magnitude on the size of network. So they were speeding up significantly in the last few years. So that's good news. So how big then? Oops, sorry. In 2025, VNN Comp featured models up to 68 million parameters. So the neural networks that I was showing you was, what, 5 parameters, yeah? And 68 million is what you can have, like if you just download the verification tools of today. Versions of these same tools developed by companies are reported to be able to handle about 350 million parameters. But if we look at machine learning world and look at this graph, we'd be able to see the growth of real machine learning models employed by big players. And we can see that in the last few years, they have grown to billions and even trillions parameters, yeah? So that is way above the best neural net verifier that we have on the market today. So that's, again, bad news. But there is good news again, and this is an important catch. At the same time as models were growing, as something else was happening, if you were just given a task, like recognize cats or pedestrians, or implement a controller, then progressively over time, you need models of smaller and smaller size to do this. And this actually gives hope for neural net verification, because this red box is now the models which are easily within reach of neural net verifiers. So realistic scenarios for verified neurosymbolic code are controllers in autonomous cyber-physical systems, because they are rarely bigger than 68 million parameters. And small language models, which are apparently on the rise. The talk is, and I'm citing here The Economist, that more and more producers will be focusing on small language models defined as models up to 4 billion parameters. The idea is, if you want to generate your AGDA proofs, you don't need the same large language model to know how to bake cakes. So you can isolate those models and have them small. And some of the big players on the market actually are recognizing this very fine line between what neural net verifiers can do and how small the models should become in order to be verifiable. So that's a new DARPA Assured Autonomy mission. If you actually look at their tools page, you will see majority of investment has gone exactly into neural net verification. And I think this is in recognition of the trend that some models are becoming increasingly smaller, and you will be able to verify it. So the future is, it is of course still early days for neural net verification, but when tools like Marabou and its successors mature, they will need to be safely integrated into trusted code and trusted verification pipelines. And for this agenda to succeed, of course, neurosymbolic code must meet proof-carrying code. There's just no way you'll be able to trust all those big verifiers without repeating the same steps that I have just shown you. And finally, functional programming and types communities have this unique expertise to make this happen. So, in my opinion, future safety of complex systems with neural components is actually a programming language challenge, because neural net verification challenge is almost there, it's almost resolved. And the next step will be people to learn to do what we have discovered with vehicle, faster, better, perhaps more elegantly than we did, because that will be really the biggest catch for safety of AI. Thank you.
Oh yeah, good, it's on. You talked about progress in the size of the model network you can verify. How much of that is just Moore's law versus how much is actually algorithmic improvement?
I'm not sure I understand your question.
Okay, you said every year we get roughly an order of magnitude increase in size in that one. Is it just because our computers are getting faster? Or do we know how much is actual algorithmic progress?
Yeah, there are heuristics and optimization techniques there. So the plain deluplex algorithm that I have shown you is awfully inefficient. And so you could implement lots of heuristics, say never explore that ReLU branch at 0 anyway, cut down that search space. It's mainly that. And of course, just improvement in computing power, but mainly heuristics.
Thanks.
So over here. So for the neural network verification bit, as I understand it, you give to Marabou or some other system a property that you'd like it to prove for a particular set of 4 billion weights.
Yes.
And then it says, yes, the property is proved, and maybe here's a certificate that you can check.
Yeah.
Okay, but then I do a little bit more training, and now, a different 4 billion weights emerging. I have to run verification all over again. That's question one. And question two is, and what if it says, oh, very sorry, I can't verify it. Might be true, but I can't verify it. Then, you seem to be a bit stuck. Shall I train it again and just hope for the best and keep, do you see, how can you guide it towards something that is verifiable?
Yes, so all you said is exactly true.
Okay.
So the assumption is we do not have any notion of a good neural network. Like all of them are equal to us as long as they satisfy the verification property and are good in optimization terms as well. So yes, we're happy to retrain as many steps as we need, and then once it's a tick, we just take that precious neural network and deploy it in our autonomous system. The earlier part of my talk was about using, specifically guiding through your compiler towards property satisfaction. So this was this bit. It's probably worth. So you can use the same vehicle compiler to generate loss functions so that you guide your neural network to satisfy the property through training. But it is not a guarantee, so it may never converge to satisfying your property whatsoever. And in that case, you just say, well, I failed. But in majority of cases, it's very efficient. So you start with, oh, this property is not satisfied, and after some training and twiddling, you make sure that it does satisfy the property. It turns out to be surprisingly easy.
Okay, that is surprising, yeah.
But we were not
certificate.
dealing with large language models or something like this. These were neural networks of small sizes with very well-defined properties.
And if you have 4 billion parameters, then the certificate of its validity
Will be
is
very
also
huge.
size 4 billion.
It will be very
So there's
huge,
quite a lot of
yes.
checking to do.
Yeah,
Okay.
it's a lot of checking to do. But it's smaller than looking for those certificates. Yeah, it's the same case with SMT solvers. Finding a certificate is hard, checking it is still much, much easier. But it's quite big nonetheless, you're right.
I'm going to ask my question by way of a concrete example because I think that's easier. Like, let's suppose that you're applying this to like some image recognition thing, right? So then your model is like your 3D world, and you can easily write a projection of that into some 2D space, which is what a camera would see, and you build a neural network on trying to recognize things in that 2D projection. Okay, so then if I understand this right, the projection of a 3D world into a 2D thing would live in E, I guess. But then, the reason we use a neural network for a problem like image recognition is that because we have absolutely no idea how to do that symbolically, right?
Yes.
So I can easily write something that renders a rabbit from a certain angle, but we don't know how to do it. But then, wouldn't you have the exact same problem when trying to write Q or P, because you would need to formulate it in terms of the 2D image of a rabbit? Because, you see what I mean?
Yes, yeah, it's called the problem of a missing spec. So for large language models and computer vision models, there is a problem. So how do you define pedestrian in pixels? How do you define a cat in pixels? If you cannot do this, this whole technology could go to the bin because our specification Q will be missing.
Exactly.
And we're done. There is no solution to this problem. That's why all examples, no good solution, no general solution. All examples I was using were controllers where the property Q is property Q. And unless you can conjure it or somehow massage it, you will not be able to apply this technology. So this is a serious limitation. So actually I cheated. I told you scalability is the only challenge. The second one is the missing spec. This limits the number of applications you can have for this.
Okay.
Thanks, Katya. That was a really nice talk. I like the way you put all the different technologies together and told us we were actually doing the right thing. But the only example you talked about was the Boyer-Moore example of a car with a little bit of wind not being pushed off the road. But where I really want to know is the Waymo or the Tesla is not going to kill anybody. Or I want to know for my large language model that's not going to advise teenagers to commit suicide. So what sort of things realistic? You didn't talk very much about what interesting safety properties we might actually be able to prove. Could you give some examples?
Yeah, so I think that's why in postscriptum I referred you all to the stool webpage of the new mission of DARPA. So my understanding is that for these to be funded and funded at a large scale, you will make the argument that I've given to you, that autonomous systems with these controllers where you have good properties, there is no reason why you shouldn't be verifying them routinely. Right? So if I can verify more and more examples and the likes at a large scale, I must be able to do it. And there was not even technology to do it. We had to write vehicle in order to handle the whole thing.
Right, but okay, now I've written vehicle.
Yeah.
What is a property of my car or whatever that I could actually verify that would be a useful safety property?
Yeah, so these will be some boundary conditions on performance of your controllers, for example. So in that sense, more and more example is exactly the indicative of what you will be able to do. So your system has some small neural net component with well-defined properties of that component, and then you verify it. It's very similar to the previous example. So if you were thinking that we'd be able to verify the computer vision unit in Tesla, we would not.
So it's something like the robot arm will not go beyond a particular bound when I'm doing automated manufacturing.
Yeah, and then if the robot arm does not go in that particular direction, then you would not hit the wall. So you take the guarantee on the neural net and then propagate it through all of your program, because if nothing bad happens with the neural net, nothing will happen with the rest of your program. That was the idea behind Boyer and Moore example. Yeah, I could guarantee complex behavior of the system if I could say that I have certain conditions on this controller. The example of Boyer-Moore is not as silly as you might think, because I still allowing quite a lot of flexibility for that neural network. I only limit it on some safety conditions. It could be arbitrarily creative and it's just here what two inputs, but there are other examples when you have controllers with many more parameters, and neural networks behave better than handwritten controllers because they give you solutions that a human programmer did not come up with. So my verification condition Q only limits some safe, unsafe kind of behavior. So that is the game there, but not verification of some like computer vision units, mainly because there is a missing spec for those. So it's not the problem of vehicle, it's the problem of machine learning, if you like. Yeah, if you don't have a specification, if you don't have a property, you're done.
Right. Okay, thanks.
Hello? I was curious if this is going to be included in things like autonomous systems like a robot or a car. Have you ever verified the actual, like, I guess, runtime characteristics of how long it would take for the neural network to run? So inclusion in, like, I guess, a real-time operating system? Because presumably if it's like, let's say a robot arm, if it needs to act within a certain amount of time, would you be able to prove properties like that about the neural nets?
You mean, will you be able to run verification real time as you drive your car?
Yeah.
You probably don't want to do it. For small neural networks, it's very quick, but the idea here is that you verify this neural network, give certificate, and then you deploy it with certificate attached.
Okay.
So that's my understanding is how it's going to proceed.
Yeah.
Okay. Oh, great. Hi, Jeremy. This is maybe going back a little ways, and I'm sorry if I just didn't follow, but the sort of reduction from your property Q to P to R, I think I didn't quite follow how you're able to generate the R that doesn't care about the embedding and unembedding at all.
Right. Well, there is a very simple type system running underneath, and there is normalization of all your. For example, in my example, there was a normalization function, so it will go and normalize, and it will work out this property R just from the property Q, basically by normalization. There's a simple type system that also checks linearity and quantify errors, but it's as simple as normalizing the stuff, basically.
Got it. Are there problems where those embedding and unembedding functions become more gnarly in some sense, or are they always relatively straightforward?
Straightforward unless your property Q is not satisfying the linearity and quantify fragment.
Okay, got it. Thank you.
Thank you. That was really incredible talk. I was wondering about neural networks that are built with non-ReLU-based activation functions. Like, what if it's something really like a bit more complex, like a hyperbolic tangent or something like that? Has there been work to handle that kind of thing?
There is indeed. I totally ignored it because the only way we could construct certificates was for neural networks. But in this neural net verification competition, there are tools that work with nonlinear functions. My guess is that it will be harder to get certificates and prove validity of what they do, but they do. There is plenty of work in it. Mm-hmm.
Wow, great, awesome, thanks.
One more?
No.
Okay. That's actually related to that one. So actual neural networks, they work with basically bits with very finite precision. but your verification seems to rely on having rational numbers. How does it interact?
Well, not exactly. So vehicle has reals.
Hmm.
So I'm citing here this paper. The trouble with floating points, reals, infinite precision reals, and then integer representations of neural networks is a huge one, and it's partly discussed in this paper. I ignore this for now. So vehicle type system as of now has reals. The Agda example used rationals. Ideally, we haven't had time to do this, but ideally you want part of this infrastructure that I represented to also take care of some of the number conversions. But actually, it's one of the reasons that some of the current neural net verifiers were shown unsafe. It's because in specification you specified it in reals, then the real neural network, actual real neural network is with floats, and then you get some discrepancy between this, and then your certificate is invalid. So these, you absolutely hit the nail on the head. If you like, that's a third challenge that exists there, is also with numerical conversions. An easy hack, if you wanted to, would be to quantize all your neural networks and do all in some quantized version so that you avoid the problem of reals floats altogether. But this is, I guess, then not a programming language challenge, but there are some interesting things to resolve with numerical representations.
Thanks.
Okay, let's thank Katja again. And it's time for coffee.
Yes.
Okay. I really wish we were in a smaller room. This is actually a very crowded, small room, but it doesn't feel like it. I don't suppose I can convince everybody sitting in the back to come to the front. Right? If everybody sat in this little square here, it would be completely full, and we would all be excited, as we should be. Oh, this is actually working. Some people are moving. This is great. Good. Can people feel the excitement building? This is great. Okay. So this is a section on something near and dear to my heart, parametricity. We have 3 papers taking quite different views of parametricity. I attached a named parametricity theorems for free, which sort of lives on. So you can see it hiding in the title of this paper. And so I'm very interested to hear. So there's a standard result that goes back before parametricity. I think due to Knuth, that says if you test your sorter on just zeros and ones and it always works, then it works for any numbers. And this is a descendant of that theorem, I think, which I'm very interested to hear about. So Kazuhiko is going to tell us all about it.
Thank you for the introduction, and hello everyone. So I'm going to present my joint work with Cyril Cohen on functional correctness proofs of merge sort. So more precisely, the contribution of this paper is modular correctness and stability proofs of several variations of merge sort. Our approach applies to top-down, bottom-up, non-tail recursive, non-smooth, smooth merge sorts, and even the ones in the standard libraries of OCaml and Haskell. The proofs are twofold. Firstly, we prove that each merge sort function satisfies what we call the characteristic property of merge sort. Secondly, we deduce the correctness results solely from the characteristic property, so the latter part of the proof is shared between several implementations. As the title of the paper implies, our proofs use relational parametricity. We formalized this proof technique in the rock prover. I believe that our characterization and proofs give clear insight into what merge sort does. So even if you don't do any verification work, I hope that this talk and the paper will help you in, first, better understanding merge sort, second, getting your implementation of merge sort right. Let's take a look at two examples of merge sort, namely top-down and bottom-up merge sorts. Top-down merge sort is the one you often see in a textbook. Its idea is to, firstly, split the input into two halves, secondly, sort each half, lastly, merge them. The recursion stops when the input is singleton. The binary tree on the right depicts an example of top-down sorting process where a branch node represents merge. On the other hand, the idea of bottom-up merge sort is to, firstly, split the input into singleton lists, secondly, obtain sorted lists of length 2, then 4, then 8, and so on by merging the adjacent pairs, and lastly, eventually obtain one sorted list. The binary tree on the right depicts the bottom-up sorting process for the same input as before. We call these binary trees showing the divide and conquer structure of an execution of merge sort traces. Indeed, these top-down and bottom-up traces have different shapes. It explains the fact that to verify several implementations of merge sort, we need to verify some lemmas by induction for each implementation. Basically, eliminating this duplication is the motivation of this work. Before defining the characteristic property, let me give the intuition behind it. The intuition is that by replacing merge with concatenation, we can turn any merge sort function into the identity function. If it is not the identity function, but may permute some items, the sorting function in question is unstable. We can easily check by functional induction that this claim holds for the top-down and bottom-up merge sorts shown in the previous slides, which are in fact stable. In the next slide, I'm going to define and explain the stability and then justify our claim. A sort function is said to be stable if it preserves the order of equivalent items. Note that equivalent here does not mean equal because we do not assume the relation to be an order but a pre-order. To ensure the stability of our two examples, we were actually assuming that they use this implementation of merge. The crucial point is that when two items x and y being compared are equivalent, merge gives precedence to x, which is the head of the first list xs. So two lists xs and ys must correspond respectively to the former and latter part of the input. Therefore, if we replace this merge with concatenation, it should not permute any item. To put it in another way, let's instantiate the comparison function with the trivial preorder that always returns true. Then merge below becomes equivalent to concatenation. The predicate equiv x in the definition above becomes always true. And so filter by equiv x becomes the identity function. Therefore, sort s is equal to s. To sum up, this instantiation has the same effect as replacing merge with concatenation and turning the definition of stability into the one, saying that sort is the identity function. Now we define the characteristic property. A function sort of the first type on this slide satisfies the characteristic property if there is a corresponding abstract sort function a sort of the second type on this slide, such that it is sort when instantiated with merge. It is the identity function when instantiated with the concatenation, and it is relationally parametric, which I will describe in the next slide. This type variable R morally represents the type of sorted list, and both of the first two conditions below instantiated with list T. However, the use of parametric polymorphism on R is crucial in making sure that a sort builds sorted lists using only three operators, namely merge, singleton, and empty. In fact, this property is ensured by the third condition, parametricity of a sort. As I said, we need to prove the characteristic property for each merge sort function. Usually, the first and second conditions can be proved by functional induction, and the third function follows from the abstraction theorem, again, which I will describe in the next slide. If this sorting function in question is sufficiently simple, the first condition should hold by definition. And it is the case for the top-down and bottom-up merge sorts on the previous slides. Parametricity is a property of polymorphic functions that they cannot inspect the type variables, and so they should behave uniformly regardless of the type with which we instantiate them. We say that a term T of type A is relationally parametric if T is related to itself by the relation square bracket A. These square brackets interpret types as relations. For example, two functions f1 and f2 of type S to T are related if it's the first case, if they map terms related by square bracket S to terms related by square bracket T. And the second case says that two polymorphic types of type fol ST are related if for any types S1 and S2 and the relation on them, F1 S1 and F2 S2 are related by square bracket T, where this square bracket T interprets S as the given relation. The interpretation of ground types such as Booleans and natural numbers is just equality. The interpretation of polymorphic container types extend the given relation in a pointwise manner. For example, two lists of type list T are related if they have the same length and their items are pairwise related. Here I present a simplified version of an abstraction theorem, which says that closed terms in the empty context are parametric. In the rest of this talk, I described the second part of the proof, that is, how our characteristic property implies the functional correctness and stability of merge sort. From the characteristic property, we derive two key properties. The first one is an induction principle over the traces of sort for reasoning about the relation between the input and output of sort. The proof of this lemma is just a straightforward application of the parametricity of A sort. We do so to show that the given relation relates the two instantiations of A sort that appear in the characterization, which I call to S and sort S. In fact, this induction principle, an instance of the general fact that parametricity implies induction principle on Church-encoded data types. As you can see, the type of A sort instantiated with concrete T and input is the type of Church-encoded binary trees. As an example of use of this induction principle, we prove that sort S is a permutation of S. For the induction case, we need to prove that whenever S prime and T prime are respectively permutations of S and T, the merger of S prime and T prime is a permutation of the concatenation of S and T. The base case follows from the reflexivity and the reflexivity of the permutation relation. Our induction principle also implies our first main theorem, namely sortedness and stability of sort. Here we assume that the input to be pairwise sorted with regard to relation 2, and then the result of sorting it by relation 1 is sorted with regard to the lexicographic composition of relations 1 and 2. While sorted means that any two adjacent items are related, pairwise sorted means that any two items that appear in order are related. In other words, the pairwise sortedness extends the sortedness with transitivity. While I'm not going to show the detailed proof of this main theorem, this is the key lemma for proving its induction case. In the proof of this main theorem, the second assumption of the lemma follows from the pairwise sortedness of the input, and the third assumption of the lemma follows from the induction hypothesis. The second key property we derive from the characteristic property is the naturality of sort, which says that sort commutes with map. Basically, this is a free theorem that follows from the parametricity of sort, which follows from parametricity of A sort. From the first main theorem and the naturality of sort, we derive our second main theorem, which says that filter commutes with sort. Here is a proof sketch in the backward reasoning style. Firstly, we replace S with map f S prime, where S prime is the list of indices of S, and F maps indices to items. Secondly, we move the application of map using the naturality of filter and sort. Here we change the relation and the predicate P with their preimage under F. That takes indices. Thirdly, we apply the congruence rule. To prove the last equation, it suffices to show that both sides contains the same set of items and both sides are sorted with regard to this strict order. Note that here we turn a non-strict preorder on indices into a strict order on indices by lexicographically composing the former with the strict less than relation on natural numbers. Indeed, we use the first main theorem to prove this sortedness condition. Stability can be seen as a corollary of our second main theorem because a list collecting equivalent items is a fixed point of sort. In contrast to this formulation of stability, our second main theorem applies to filter by any predicate P. In the paper, we argue that our main theorems are more general than this corollary. Let me briefly go through the rest of the paper before concluding this talk. In section 4, we extend the characteristic property to support tail recursive merge sort, which requires tail recursive merge, and smooth merge sort that reuses sorted slices in the input in the sorting process. In section 5, we explain technical aspects of our rock formalization. The first one is a technique to make merge sort structurally recursive so that rock does not ask us for a termination proof. The second one is the interface for stable merge sort function, which enables overloading of our correctness lemmas through so-called canonical structure. The third one is automation of parametricity proofs using the parametricity translation. In section 6, we discuss the limitations of this work. Most notably, we didn't find a way to prove the characteristic property for the merge sort function of recent GHC due to its merge function that takes 4 lists instead of 2 lists. Let me conclude this talk by abstracting out a merge sort function and re-instantiating it differently. We obtained the identity function. The characteristic property implies the 2 key properties of merge sort that are sufficient for proving the functional correctness and stability of merge sort. The first key property is the induction principle over the underlying binary trees or traces of sort that relates the input and output of sort. The second key property is the naturality of sort, which is a free theorem. That's all I have for you today, and I'm happy to answer your questions.
Okay, we've got a couple of mics available. So I'll ask a first question while people rush towards the mics. Can you go back to the slide where you gave your stability theorem, the key theorem?
The definition of the stability, you mean?
The theorem, I think it was.
Theorem, stability as a theorem.
No, the one where you said if it's relational, the one where you gave the 3 properties that needed to be satisfied.
Okay, you mean the characteristic?
There you go, that one.
Okay, yes, this.
So there's something I'm slightly confused about, right? It says this will satisfy the CP if these 3 properties hold, and I think I see part of it. So what I was worried about is you say it's relationally parametric, so that gives you things about all sorts of things. But then you were instantiating these, right? And A sort can satisfy those if it ignores its second and third arguments.
Sorry, say it again.
So it looks like we're saying, okay, the first argument is how you combine stuff. The second argument is what you do to make a unit list. And the third argument is what you do to make the empty list. But
yes.
Oh, I understand what's going on. So I thought, but you could just ignore, right? You could easily satisfy the first two properties by ignoring your second and third arguments.
The second and...
But you can't, in fact, satisfy by ignoring the second and third arguments because it's got to be polymorphic. So you couldn't instantiate the second, you couldn't just replace using the second and third arguments by the unit list function and by the empty list function, because if you did, they'd have the wrong type.
Right.
So, okay,
yes.
I answered my own question.
So
Thank you.
basically, merge singleton empty are constructors of sorted lists here. So, and we wanted to make sure that this A sort builds sorted lists only using these three constructors.
Okay, and no other questions? You were too clear.
Maybe.
So you talked about this in general, and the general property is, of course, right, the whole point is it's very general, so it works for lots of things. But what's an instance of a useful theorem that you got out of this? Right, so a particular kind of merge sort has this property?
Not really. Like we just have general theory of merge sort that applies to any instance of this characteristic property, and I don't really have like lemma about merge sort that is really specific to like one implementation or one particular kind of implementation. I don't have any example.
Right, so the quicksort people made good use of the fact that, does next person want to come up and start getting ready? Are you going to do that? Good. So why don't you come up and, you don't want that bright light in your face? Go ahead. Good.
You're right. Yeah. Okay,
Now you
cool.
can.
Thanks for the talk. Maybe a naive question, but could you do this for other types of sorting algorithms?
Right. So this characteristic property also applies to insertion sort, like correctly implemented insertion sort that is stable, but we don't really have not only sorting algorithms, but we don't have any other kind of algorithm where our proof technique works. So that would be the honest answer. So we just don't know.
Okay, thank you.
In your formalization, do you rely on any axioms?
No, not at all. So, so for maybe one concern is the parametricity proof, right? So, okay, should I discuss? So I actually have.
No, you have to unplug because he's going to plug in while you answer. Or do you have a slide that answers it?
So yes. So the thing. So the thing is that for parametricity proof we use parametricity translation. So it takes a term and produces its witness of parametricity represented as a log term.
So you can do this because you work with closed types, so your proof is not parameterized over like any
Right.
type with an ordering or something like this, but you work with some concrete types, right?
Yes, exactly.
So if it was more general, then you would need an axiom.
Yes,
Yeah.
yes, I think so.
Yeah, thank you.
Okay, so where do you want me to? Okay, thank you.
Thank you.
Okay, so our second talk is about CRDTs. Parallelism is just really hard. And there's this whole family of things called CRDTs that give you a sort of uniform approach to parallelism for a wide, not everything, but a wide range of things. So I always think, oh, I want to understand more about CRDTs. And one of the important things in computing is to relate different approaches. Right, so what's the most important thing about Turing machines? That they have exactly the same computability power as lambda calculus. So there's two standard approaches to CRDTs, and this is going to tell us something about the equivalence between them that's well known, but making it formal and something that you can actually prove and use. So I'm very keen to hear about this.
Hello. So hi everyone, I'm Nathan Lichwager. I'm a PhD student at University of California, Santa Cruz. My advisor is Lindsay Cooper. So like was just said, I'm going to be talking about CRDTs, conflict-free replicated data types. So I'll begin with some background. If we have a, say, web service or some kind of service, and we want it to be more available or more fault tolerant, we would replicate this service across different nodes on a distributed system. We can represent this service usually as like a state machine, which is what our perspective in the paper. So here is just replicas 1, 2, and 3 at US West, US East, and Oceania, for example. Okay, so a nice way of doing replication is with these conflict-free replicated data types, and there are largely two flavors. There are the op-based CRDTs, which they enforce consistency among the nodes, meaning they all have the same sort of results to queries. They enforce consistency by ordering the updates between them. So when a replica has an update, it will then propagate that update to the other replicas, and there's a partial order, usually called a causal order, that says these updates need to be applied in this order. So roughly each replica is executing the same updates in the same partial order. The concurrent updates are allowed to commute. So the other flavor are the state-based CRDTs, which they enforce consistency by requiring that the state space is a joined semilattice. And then they propagate their states to the other replicas. And since it's a joined semilattice, as long as they can perform a merge, if all the replicas can mutually merge with each other, they will eventually converge and give the same state. Here's just like a little example. So on the left here, we have the op-based CRDT. The example, by the way, is a grow-only counter. So our state space is just the integers. So on the left, we have an update, increment 5, at replica 1. It propagates that update to the other two replicas. And then replica 2 increments by 7, and then also propagates those. Those updates get executed, and then at the end, we have that each replica has a state of 12. On the right, we're also doing a grow-only counter, but now we're taking a max as a way to do the merge. And when you are taking a max between 5 and 7, obviously 7 is the larger number, so we end up with a final state of 7 at each replica. So even though these are both sort of implementing the same data type, and they have the same client-supplied updates of increment 5 and then increment 7, we can end up with different states. It was this sort of example that we first noticed that maybe there's some nuance to the way that they are equivalent. So we thought, like, okay, in what sense are these CRDTs actually equivalent? We know that from prior work, Shapiro et al. In 2011, that there are translations to transform an op-based CRDT into a state-based CRDT, and then a state-based CRDT into an op-based CRDT. Of note is that these translations are not inverses. So if you go from the left side to the right side and then back to the left, you don't get back the same CRDT. It's actually something different. What Shapiro showed in his paper were that these translations preserve strong eventual consistency. So if you take your original CRDT, translate it into the other kind, then the result still exhibits strong eventual consistency, meaning that when updates at replicas cease, and then the replicas are allowed to communicate with each other, they will eventually converge to the same state. But we were kind of curious about sort of non-converged behavior, because in a lot of distributed systems, you don't actually stop local updates, right? Like you allow clients to be always providing updates. Oh, right, and then one other thing that I wanted to point out is just that strong eventual consistency is perhaps not quite enough, because a mapping which would also preserve strong eventual consistency would be a trivial mapping that takes a CRDT and then maps it to a data type with one state and updates do nothing. That's converged just immediately. So somehow preserving strong eventual consistency may not quite be enough. So even though we have these questions, we saw in the literature that sometimes there are assumptions that one can focus on one type of CRDT and sort of ignore the other because we have a translation between them, and it's taken to be equivalent. So in some sense, we saw that this claim of equivalence to be load-bearing, even though we're sort of interested in, as programming language people, what observational equivalence really means with respect to these data types. So what do we mean by the same? If we have op-based CRDTs and state-based CRDTs, what is the real sense that they are the same? So we have here sort of these computational trees. On the left, we have an op-based CRDT. On the right, we have a state-based CRDT, and then the initial state and a path down to a converged state. The intermediate paths here are possible computations that could happen. So it seems obvious from Shapiro's work that there should be some kind of simulation between the initial states, where all the CRDTs have all the replicas have the same state, and the converged states, where again all the replicas have the same state. But what we were interested in are whether we could put these intermediate states inside a simulation as well. So our first major contribution with this paper was showing that, in fact, you can. If you take a given CRDT and then translate it, you can construct a simulation, two simulations actually, from the original to the new CRDT, and then the other simulation from the translated CRDT back to the original. We proved that you can construct these simulations. The main focus of the paper, we do have in the appendix both translations, but the main focus in the main paper is the translation from op-based CRDTs to state-based CRDTs, because we found that to be the more interesting case. Our second contribution was leveraging the first one. So once we know that we have these simulations, we were able to define this sort of simple imperative language, which allows a programmer to interact with CRDTs through while loops, updates, and queries, and then show, there's also a variable store, and then show that if we have a program P running with CRDT A and that program terminates, then if we translate CRDT A to CRDT B, that program will still terminate. And then this also goes in the other direction. So it's actually a co-termination result, meaning that we can't actually construct a program to differentiate the original CRDT or the translated version. So in that sense, they are equivalent. What I wanted to talk about, though, for this paper was really the simulation proof, kind of the key idea how we wrote the proof, because it's largely, our second contribution relies on that simulation existing. So that's what I wanted to talk about here. So let's take a closer look at the translation. We're focusing on the translation from the left to the right, so the G. given an op-based CRDT, it's mostly defined by these two functions, prepare and effect. So prepare takes an operation and the current state, and then it generates a message which contains the effects of that operation. And then there's the effect function, which takes the current state and a message, executes that message, and then updates the state. Local updates are defined as a composition of prepare and effect. So when a client does a local update, prepare happens, immediately effect happens, and then the message is sent off. And then the other replicas will use effect. The state-based CRDT is mostly defined in terms of the joint semilattice and merge. So the normal translation that you would use here is, for the state-based CRDT, we would represent the state as sets of messages. When we do a local update, we delegate to the underlying op-based CRDT to generate a message and then add that message to the set. We made a slight change from Shapiro's algorithm. So Shapiro gave an algorithm from op-based to state-based and then one from state-based to op-based. We made a small change where we interpret the sets of messages into states kind of on the fly. This is not a very, oops. There we go. This is not a very efficient way of doing this translation, but it's nice to work with theoretically. So the basic idea is if you have a set of messages that are partially ordered, you can then partition that set into sort of grades, where in each part of that partition, all the messages within are concurrent. And then we can just take any message from that grade and then apply it. And so this lets us define this interpretation function recursively. So just to say again, we're being given an op-based CRDT, translating it to a state-based CRDT by representing the state as sets of messages. And the only thing we need to remember was the initial state. And we just translate to the current state by applying all those messages. And the definition of simulation that we use is the somewhat standard one. So we're focusing on this talk just the simulation with a given op-based and then the translated state-based. We allow one CRDT to take a step where that step is defined as either an update, a delivery, or a query. And then we construct a matching set of steps on the other CRDT. Technically, we're using a weak simulation in the paper, but just for this, we're not going to get into the exact details. Much more of a high-level take here. So when we were constructing this simulation, we came across an example like this that sort of shows the simulation is sensitive somehow to the network semantics of our CRDT. And this is really what led us to the question, what is the sense that these two kinds of CRDTs are equivalent? So at the top, if we were to have an op-based CRDT doing an increment 5, broadcasting that update, then in increment 7, broadcasting that update, then the other replicas have two possible messages that they can deliver. They can deliver an increment 5, and then they deliver an increment 7. It has to be in that order due to the causal ordering, the partial ordering on these messages. But in the state-based representation, we need to be a little careful about how we send state to the other replicas. So for example, if we do increment 5, then increment 7, we can end up with this state that contains two messages. If we then broadcast that, the other replicas can only merge that state, which contains both messages. If we then interpret that into the op-based state, then we somehow jump ahead, right? A replica on the op-based side could show a state of 5, but a replica on the state-based side would only show 12 or more. So in some sense, we have to be a little bit careful about how the communication between replicas works. OK, so I'm going to show the two sort of main steps in the simulation. So we're going to first look at the op-based CRDT simulating the state-based one. So given this op-based CRDT, we construct the state-based version of it, representation of it. And we'll say that H and S are in simulation if we can interpret H into S. There's some side conditions, but for the purpose of this talk, we won't get into that. The critical step for this is how we simulate merge. So if the state-based CRDT performs a merge of a set of messages, we need to simulate that on the op-based side. This is weak simulation, so we're allowing multiple steps. More or less, we're going to be picking out the messages in that set and then delivering them one at a time. It's a fairly straightforward argument. The somewhat more interesting direction of this simulation is showing how the state-based CRDT simulates the op-based one. And again, we're looking at how delivery of messages works. So suppose the op-based CRDT delivers a single message, M. The state-based CRDT can only merge a set of messages. So we need to simulate the delivery of one message by merging a set of messages. And we need to be careful to not overstep somehow. The way that we sort of think about this is whatever H chooses to merge, whatever that replica chooses to merge, we want its state H to somehow already know about messages 1 through mk minus 1, where the m sub k message is the one that contains the effects we care about. The way that we do this is we sort of restrict the state-based CRDT to always broadcast just as frequently as the op-based CRDT. So by constantly broadcasting just whenever the op-based CRDT does, we will guarantee that replicas have access to a number of states, and then each of those states is sort of growing by one message at a time. So then if we look at a replica, and that replica wants to deliver messages M1 through M3, for example, M1, M2, M3. Remember that these are ordered by causality. In practice, we would use something like a vector clock. The order that has to be followed is you first deliver M1, then you deliver M2, and then finally you deliver M3 in this example. On the state-based side, we would simulate by merging the set that contains M1, then the set that contains M1 and M2, and then the set that contains M1, M2, and M3. And so at each simulating step here, the replica, the state-based replica, knows about the messages that happened before the message we currently care about merging. So with M1 as the first message, there's nothing to know. With M2, that replica already knows M1, so when we merge the set M1, M2, the only observable change comes from M2, and so on. And that's essentially the heart of that proof, is by checking the existence of these sets, making sure that they're available, which they are because we're forcing broadcast to happen very frequently. So that's more or less the heart of our proof. And much of the other contributions in our paper relies on those simulations. So our conclusion here is that the observational equivalents of CRDTs are somehow sensitive to the network semantics. So if you want to say that a CRDT is equivalent and we can ignore the other type of CRDT, then you need to somehow consider the network semantics involved and make sure that broadcast is happening just as frequently or something similar. Nonetheless, if you know that the communication semantics in both kinds are roughly the same, broadcasting just as frequently, then you do have an observational equivalence in a formal sense. And because we have a pair of simulations, we actually obtain a trace equivalence, where we're looking at traces of updates and queries and the values returned by those queries. So if you have a safety property defined on a trace, then that safety property really will transfer via the translation, the CRDT translation, because we have that trace equivalence. And then also we have our co-termination result, which was not the focus of this talk, so if you want to see the details, you can check out our paper. And yeah, that's what I wanted to talk about today. Thank you.
First question.
Hi, I'm May Milano, Princeton. I am curious to know if you also have sort of the equivalent negative result, which is that there is no possible encoding of op into state or state into op, such that you could get simulations without being sensitive to the network semantics, as in the network semantics simply must matter.
Oh, that's good. I guess we do not have the equivalent, the negative result as you just said, but I see no reason why we couldn't leverage the same techniques we used here to construct it.
Negative result would actually be true, that the network semantics are fundamentally important.
We definitely believe that they're fundamentally important, so let's talk.
Okay.
Thank you.
Hello, Henning Obert, VO Erlangen. You told me earlier that you, in the end, decided against a co-algebraic approach.
Yes.
But could you do it? So is there still a functor in the lifting that makes your simulations co-algebraic simulations?
So could we do it with co-algebraic simulations?
Yeah, exactly.
I think so, because we don't show it here in the talk, but in the paper we have a semantics for the network, which you can define as a co-algebra pretty easily. It would be like a step into the power set of the states. You could use like the saturation definition of co-algebraic simulation. You could obtain it that way. Yeah.
Okay, nice. Thank you.
Thank you. Nice question.
Hi, thanks for the talk. I was wondering if you had, maybe I missed it, or if you thought about like a sort of result along the lines of the network semantics matters, but if you allow arbitrary merging rather than sort of the ordered merging, you used to get like a soundness or something where it's like you're at least like you're reducing the space of behaviors you see.
So I haven't thought of doing it like that, but I think there might be a way. I think maybe I might need to ask some clarifying questions. So if you want, we could talk a little more.
Sure. I did have one more question if there's a moment. It seems like what possible use for this would be like compiling things. Like if you can sort of specify whichever kind you want and then use this to translate into like the appropriate runtime version. Have you thought about like the performance if you were going to do something like that?
So strictly speaking, no, we didn't think too hard about the performance because we wanted something that was sort of nice to work with theoretically, even if it would be inefficient. There is a more efficient way of doing that translation, which it is actually more or less what Mark Shapiro did in his paper. There's just like a slight, it's just slightly more difficult to work with. But for compilation, I think it would be hard because if you're going to represent states as sets of messages, then that state is going to blow up over time. So you would need some way to forget the past messages and shrink the states. But there might be a way. Yeah.
Thanks.
So I see somebody queued up behind you who hasn't asked a question before. Did you want to ask a question?
Hey, so thanks a lot for the talk. I enjoyed it. I guess so the two translation functions that you had, you named them very suggestively as G and F. So are they in fact adjoints? And I guess the other question was, if there is an adjunction, do you also have like another adjunction? Like, do you have a triple or what's the?
Could I change your question to, is there an adjunction? Because you didn't say that.
So I probably don't know enough category theory to really answer that question. Certainly it's been pointed out before that it looks like an adjunction. So there might be, if you know enough category theory, maybe we can figure it out.
Okay. So we're running about 5 minutes late, and that was because we didn't have many people here at the beginning. So you can blame me for starting late. You can blame yourselves for showing up late. But please don't blame the speaker. I know when lunchtime comes, people think, oh, it's time to go, but we started 8 minutes late, so give him that. So theorems for free was already mentioned, and the core of theorems for free is a bunch of commuting squares. Now this is a Perl, and I love Perls because often rather than having a complicated new idea, explaining an old idea in a simpler way is just a huge advance, even though we tend to value complexity rather than simplicity. I would like to see us, as I said in my talk yesterday, put more value on simplicity. So I'm excited to see a Perl, and it seems that the key idea here is instead of, to communicate well with other people, you don't call it a commuting square. You call it a magic square. So.
Yes. Thank you for the this wonderful introduction, because that's actually the topic of the talk. Simplicity eventually wins, but it has a cost, and it's sometimes you need to widen scope. So sometimes you are in a cage, and the thing is complicated, and if you open the window, okay, then it gets you get fresh air. Okay, we know that this is that things start complex and then later to become simpler as our knowledge about it improves. But we have examples in mathematics where, for instance, in trigonometry, the extension of exponentials to complex numbers makes the whole thing much more appealing and easy to. So that's the thing that we are going to do here. There is this book which was, I think, written more to be respected than to be loved, because when you read it, it's. But it has a very important message. Is that the book is about category theory, and people always read the first part and they don't read the second part. And the second part is what matters, because there is a move from categories to allegories, and this wider scope makes things more interesting and easy to cope. In functional programming, we deal with functions, but we all know this, that functions are special cases of relations. And let us see what this brings us in this talk. This talk will have an example. Actually, the example has many details, which I hope you don't mind I go through with not in much detail. But I remember this piece of conversation walking with Simon Peyton-Jones. I'm a formal methods background, and my question was something like this: what I find lacking in functional programming practice is formal specification. And Simon's answer was, but types are the formal specifications, aren't they? They are, but it took me 20 years to understand this, okay, fully. So the title plays with this geometric construction, square. Square has vertices, labels. Let us orient them. Now we have two paths to go from B to C, and we should be able to talk about them. In particular, we should be able to compare them. This symbol of comparison suggests some kind of set inclusion. The labels are going to be relations, and this is the magic square, okay? Where does this square comes? It's a semi-commutative square. This name comes from my lectures, because throughout time, eventually I started to use these squares, and they explain things a lot. I'm going to give examples about this, some of them. And then the term magic arose. Of course, I have to be specific about what inclusion means, is the normal inclusion of relations. We don't treat the relations as set of pairs. We never say the pair 0, 1 belongs to less than equal. We say 0 is less than equal than 1. So this infix notation is the natural language for relations. John loves Mary, okay? The relation is infix. And the composition of relations is what you'd expect. So the magic square is actually an abstraction, a graphical abstraction for this formula. So it hides three quantifiers. One universal quantifier and the two existential quantifiers, which are the little dots of the relational composition. In the square, in the main diagonal, you have the universally quantified variables, and the other diagonal, you have the existential ones. It's a simple formula, but it has a lot in it. So there's lots of things that we can develop. These squares compose vertically, horizontally. There is the identity square, of course. And this is very important. This is where scope widens. You can invert them. There is a converse notion. In relations, you can always swap the two elements being composed. John loves Mary. It's equivalent to Mary is loved by John. This is a passive voice in our language, which corresponds to converse. And this is the big advantage of relations. Functions, you cannot invert them. You can only invert bijections. Otherwise, you go out of the functional world. So this is the thing. The extension is this one. And also, you can these things extend them functorially. So you can promote, in the same way you have maps and F-maps in functions, you can promote relations to structural relations. There is some technical details. This is called, in that book by Fried and Skedroff, a relator. So the square expands. Any square expands through this functor. Well, it needs to be monotonic. But now, some relations fit into these two squares. So the little, the circle means converse, that passive voice. If you apply those formulas with the quantifiers and simplify, you realize that the first square here means that the relation is total, and the second square means that the relation is univocal. This is where functions live. So functions are exactly those relations that satisfy these two squares. My convention is to use uppercase letters for relations and lowercase letters for functions. Now, if a function, now we can call it, fits in these two squares, then there is this equivalence of squares, which let us trade a function and its converse. So you see that this function slides to the bottom, okay? And so this is a replacement between this f and this identity. This is called a shunting rule, and it has a lot of nice consequences on the reasoning that we can do with this stuff. So you can always, and it's also reminds, for instance, in the classroom, of these things like, solving equations, passing terms to the other side of the equation, changing the sign here. Changing the sign means changing the relation, or in this case, function, to a converse of a function. This has a number of nice consequences. Comparing functions is the same as their equality. And some patterns involving converses of functions are so they get simplified, and you don't have any quantifiers at all. So the existential quantifiers go away, and this is a real big advantage in this reasoning. So a very common pattern of these magic squares involves two functions, f and g, and the vertical arrows. This means that there is a structural relationship. So the R-related inputs lead to S-related outputs. So this captures a higher order relation on functions, and it's quite interesting, this higher order relation, because it enables us to start thinking about types, as we're going to see briefly, as these exponentials. So you have a number of properties of these exponentials, and we can either use arrows or we can use the exponentials as we find more convenient. So some of these exponentials, so let us go back to the definition, some of these exponentials here may involve only functions or converses of functions. That's what I was going to show here. These are special cases of those exponentials, and in some cases you actually have those. So they are higher order relations, But in particular, they can be higher order functions, and that's what you get in this pattern. So if you converse the exponent and keep the function on the basis, then you get functions. So here you have precomposition, post-composition of a function as a special case of these exponentials. Of course, relational exponentials may involve other relational exponentials, and we write them in the way we like. So you can use arrows, or you can use exponentials. So here is an example of a higher order square, and we call them Reynolds squares because they're going to play a significant role in the application of, in the instantiation of these squares to free theorems. But if you see the shunting rule at work, it moves, then the nice rule, and you get what you would expect. R-related inputs, and then another pair of inputs related by the exponent, and then the output of the two functions are related by the basis of the exponentials. Sometimes it may happen, so I'm shrinking, it may happen that the two functions in the magic square are the same, or in the Reynolds square are the same. In this case, you can abbreviate the square by writing that the function f has a relational type. So now types are becoming relations, which is actually the message of this whole thing. So you write, you see the relation R on top, the relation S at the bottom, and the function going vertically. So why not write f is a function from R to S. So R-related inputs lead to S-related outputs. And types in this view are relations. And this is a very economical way of saying things. For instance, in this case, the first example tells us that the function is monotonic. And it reads well. So the less the input, the less the output. So if you want to say that the function is periodic, what you are going to say is that, you know, adding the period to the input doesn't change anything on the output. Saying that the function is constant means that whatever happens to the input, the output does not change. So it's a very meaningful, it's easy to go. So actually this forms a category, so these relational types form a category. It's actually a category identified by plotting a long time ago. The relational type is the Hom set, the corresponding Hom set, and it is Cartesian closed, and you have currying and uncurrying and all that. Of course, when you talk about uncurrying, you have the product of the relations, which is the tensor product. Another interesting thing that this relational view has is that relations are dangerously close to matrices. Okay, and so this evolves quite easily into the linear algebra setting. So now the rest of the talk is going to be about a special case of the use of these squares, which is the free theorem. So if you have a parametric function from f of x to g of x, the free theorem essentially says that the function has this relational type. And exploring this relation type is going to tell us a lot about the function itself. Because relations are very wide. So from the empty relation to the top relation, we have a complete Boolean algebra of special cases that we can use. Now I'm going to show things not going through the details, but basically going through the spirit. So suppose you have the Haskell, the const function in Haskell, from A to B to A. How much is in this type? Well, the free theorem is just saying that const has this relation type. You have the square there, and now you can perform your reasoning graphically. For instance, let us instantiate R by the identity, and then use the equivalences between the squares, and then do the shunting square, and there we are. We get this. Now, when we look at this, we see that we don't know anything about this const function. Suppose it was called function theta. Okay, const you already know is going to probably want to specify a constant function. But call it theta. You don't know anything about the function. So what we have here is that for whatever s, the passive voice of const a and composed with const a is larger than that s. A relation that is larger than any other relation is the top relation. Is the largest possible. So we can say that that pattern there is the top relation. So the square captures the top relation. And this pattern, f converse composed with f, is known as the kernel of a function. And the kernel of a function is a relation that measures how injective the relation is. The larger the kernel, the less injective the function is. So we can actually say that const a is the least possible, is the least injective possible function. So it's going to be a completely non-injective function, which is actually what the constant function does. Maps everything to the same. So there is only one equivalence class in the kernel. So other examples, okay, which of course this is the standard use of the free theorem, but they can express graphically. Flip is another example. Is going to be used later in my examples, of course you can derive properties of flip using this. Now the main question of this rest of the talk is, since types are higher order squares, how much is in a type? And it is quite a lot, more than I thought 20 years ago. So, the example is fold right and fold left. But I'm not talking about lists only. I want to range of the Haskell data foldable class. So I may not be talking about lists. I'm just talking about this interface in the foldable class. I know that the types are this, and let us see how far we can go knowing the type of the function only. Okay. Here is the two squares. The type in it has two squares. The first square is kind of a precondition for the second square. Here they are. Now some instances, instantiating the relations with functions, identity, and we get for the foldable class this fusion law that is proved in the Bird and Jeremy Gibbons book for finite lists. So we repeat the same thing for fold right, and one of the squares is the same, the other is not, but we are led to the fold R fusion law proved by Bird. Okay, a special case of this square is when the two functions are the same, let us call it S, and H is S of A, so S is higher order, so let us pass a parameter. And this becomes interesting because this precondition square is called, states the property of permutative. S is a permutative function. So the order of the arguments, when you have two S's, so S of X of S of A of something, you can swap X with A. And this is going to play a role in the example that I'm going to be. So this is the permutativity property that Olivier Danvie identified. If S is associative and commutative, then it is permutative, but not the opposite. So looking at these interfaces, when does a fold left equal a fold right? So looking at the types only, the hint is that we need to flip. I'm using this tiled to. You need to flip one of the functions. This is the best we can have. Okay. So, but under what conditions are the two folds the same? Free theorems always relate to instances of the same parametric function. So maybe we can find a universal property. Well, and this is when you need to be a little bit more less general. Maybe we need this property. Maybe we need to be sure that there is an alpha and a gamma, that when you fold over those parameters, you get the identity. What does this mean? This is the reflection property. And the reflection property gives us access to the type itself. We don't know which type do we have, but we know that it has two constructors. Alpha and gamma are constructors of the type. So then then we instantiate F and E in general with these alpha and gamma constructors, and we get this implication. Now let us introduce, that Y of gamma. Let us call it Z, and drop the two XS that represent input data structures. So fold RGX is the unique solution for H in the equations given. Substitute the equations, the solution, and we give a definition of fold R. So we get from the type of fold and this assumption that it will have two constructors, alpha and gamma, that reflect. From the theorem alone, we get the definition. And maybe we get more, because actually we get universal property, we actually get universal property of fold R solely from the type, the parametric type. What about fold left? Well, fold left is well known that it can be represented as a fold higher order fold right. Let us skip the details. The details are here. The advantage of defining fold left, which we don't know anything about, as a fold R, is that we can use the universal property of fold R to find universal property of fold left, and indeed it is here. So we get universal property of fold left. So how much can we go without actually knowing the body of the function? It's quite a lot, okay? So from the type, we already have universal properties. We already have the definitions of the functions. So under what condition does this equality hold? A popular assumption is that fold left and fold right compute the same output when the binary operator is associative and E is its unit. However, here are two examples of fold left and fold right being the same, and the binary operation is not associative, and the other parameter is not the unit element. It can be any number, okay? In this example, which is a numeric number. So what's going on here? Well, we can ask fold left universal to find out the answer. So let us find under what conditions this equality holds. This is standard program calculation work. So we reach a stage where we would like to have a swap between the fold and the flipped function. So let us recall this result, the permutativity squares, and realize that if the F is permutative, then we can swap the fold rights. So we do that. Okay, we do that, and we realize that it's because of that F being permutative that the equality holds. And so finally, let us. So how can we be sure that the integer division operator is permutative? We can try and prove, but it is an if-then else. It normally is an if-then else. If something, no. Better than that, and this is the top class magic square, is the magic square that captures the Galois connections. And the interesting thing is that integer division is the upper adjoint, whose lower adjoint is multiplication. Multiplication is easy, integer division is hard. It's normally these things happen. And about multiplication, we know that it is commutative and associative. So we play this trick of using indirect equality, and we show that indeed integer division is permutative, so fold left and fold right are the same. So this is not new, knowing that permutativity is enough for fold left and fold right being the same, but Olivier Dandy in this paper does it completely different because he postulates it, while in this view it is an outcome of the free theorem. So simplicity eventually wins, I mean, at least in my teaching, this is going to be a process whereby these things are becoming more and more accessible, but we need to widen scope, okay? And so in 1989, this paper changed the world, at least for me, okay? At least for me. And I think that's very interesting that years pass and more things come out of this fantastic result. For instance, when you have the free theorem of a recursive function, you don't even know that it is recursive, okay? So from the type, you don't even know that it is recursive. So you can actually, for instance, for the empty relation, you get the base cases. Quite interestingly, when you instantiate with the top relation, you find the situation where the function doesn't change the topology. Okay, that changing things but keeps the topology. Very interesting stuff. So thank you for your attention. Okay.
Right. Are there any questions?
So thanks for the talk. Yeah. So you raised the questions last, say when the fold R and fold L are equal.
Yeah.
And you give just a sufficient this is sufficient condition, right? If F this
is permutative, yes.
Is permutative, then
yes.
fold L and fold R are the same.
Yeah.
So have you thought about the sufficient necessary conditions for that?
No, I don't think it is necessary.
Yeah. So this talk also, I think, also relates to the first talk today in these sessions, I think. So I believe you know that means fold L and fold R are the same, that if and only if these functions can be represented by map and reduce.
Yes.
That means a homomorphism.
Yes.
So this if and only if. Yeah. So actually, I think that the merge sort is actually a sort of homomorphisms. In a sense, it's a singleton, empty, and sort of join concatenation, right? So I'm not so sure if your theory can also derive such kind of things. You know, Jeremy gave a proof of such kind of things. Whether your squares can help to, that means derive such kind of say. People call it the third homomorphism theorem. Yeah, maybe you can do that. Yeah,
but
just
but there is something here which is more general than that. I don't know what the data type is. I just know that it is a foldable data type.
Right.
So I need to shrink to lists, and then
right. I'm not so sure whether the free theorem can help for that. You're right.
Yeah. But I don't even know. Maybe it's a foldable type.
Sure.
Okay?
Yeah. Okay. Thank you very much. Yeah.
Okay. Last question.
Thanks for the great talk. You mentioned there is a connection to linear algebra. Do you want to say a few words about that?
Yes. I mean, relations and matrices are form categories, which are monoidal categories, and they share a lot in common. So actually, I would say that I mean, relations are Boolean functions. So matrices are. I would say, but that this free theorem can be generalized to matrices. So basically what the free theorem says is that because it is agnostic on the parameters, what the amount of information in the input has to flow to the output, and that information can be quantitative. I don't see a reason why it doesn't work. So that's a topic for future work to extend free theorems to the quantitative side. Yes. Yeah.
Thank you.
Okay, so we should wrap this up. I do want to point out, in the interest of truth, that the photo that you had of me was not from the year that you talked to me, nor was the photo of Simon from the year that you talked to Simon.
I'll dig the archives.
So, thanks very much.
Okay.
Yes. Is Rutger Bröckhoff in the room? Great. Okay. Wait.
Mic check.
Welcome to the session on separation logic. So our first talk is by Remy, and he will tell us how to scale program logics to realistic functional programming languages like OCaml.
Okay, thank you. So I suspect that reading this title, most of you understand what I mean by formal semantics. Most of you understand what I mean by program logics. And if you have one burning question, it's what do I mean by a fragment of OCaml? The short answer is a realistic fragment. We're looking not at a toy model, but we're trying to modelize the real language. And the more detailed answer is, generally for this project, we're looking at OCaml without the object system, and OCaml without the type system. We have an untyped semantics. For this talk specifically, I should say everything else is fair game. That means concurrency, that means all the new features of OCaml 5, all the pattern matching stuff, everything. So for this talk specifically, we'll be covering a sequential fragment of OCaml 5, specifically including the new effect handlers. That'll be one of the main focuses of this talk because they may be semantically not so obvious to model. So what is Osiris? What do I want? I want to be able to take OCaml files written by engineers, to translate them into an embedding in Rock, and then I want to be able to prove things about this embedding using a strong separation logic like Iris. This is our goal. And immediately, this actually enforces some design constraints onto us, specifically at the level of the semantics. Speaking of the semantics, there is the question, where will we be getting our semantics from, right? OCaml has the reference compiler. It has the language manual. Unfortunately, neither of these are much help. This is an excerpt from the language manual. They're not formal. It's a natural language description. So it'll be down to us to modelize the semantics. So this project has two main parts. The first is we're actually modeling the semantics of OCaml. That's a goal in of itself. And the second is we'll be building some program logics on top of these semantics. So I talked about some design constraints. Specifically, we need to satisfy these three goals. The bottom two are imperative. We need a semantic model that's expressive enough for us to model everything we want to model. Specifically, I'm thinking of effect handlers and concurrency. We need it to work with Iris in order to write our proofs. But then because OCaml is a rich language, we really want a semantic style that scales. That's what I mean by aesthetic, something that's modular, something that composes. We want to be able to define all of the constructs of the language independently and then stick them all together. So we want to be square in the middle here. Maybe to illustrate where some traditional styles would fall on this graph. In my mind, something like small step semantics would fall at the bottom here. They're expressive enough to express all of the things we want. This is a typical Iris style. More recently, we've seen a more denotational approach with things like I-trees. The problem with these is it's not yet understood how to do things like non-local control, like effect handlers and user-defined effects. In effect, our approach is actually going to end up being a hybrid of these two, as you'll see a little bit later. And I hope to convince you by the end of the talk that we'll be reaching these goals. So we've set the stage. Let's delve right into our semantic model, especially this first part, which is we have a layered monadic definitional interpreter for OCaml. Layered because we've got this top level, which is an interpreter, written in a monadic language. That's the bottom layer. We've built up on this monad that we call micro. So this top layer relies on effects provided by the monad. So we're writing our interpreter in monadic style. And in practice, we have this monadic combinator API that makes it so we're agnostic to the implementation of the monad below. We just have these nice combinators we use for the effects we need at the level of the implementation of our interpreter. These effects are things like state, things like non-determinism, things like exceptions, etc. So what we're going to do is going to zoom in to this top level here and have a look at what the interpreter actually looks like. It looks like a structurally defined function in rock over some OCaml expression E of the surface syntax. If we look at the type here, you'll notice we have a environment-based semantics. And the return type here is parameterized by a type of values and a type of exceptions. Our type of values is purely syntactic, right? If you look, for example, at the closure here, the closure is just a triple with the environment that it captures, the name of its parameter, and the function body. In fact, here's internally the definition for function application. Immediately, you'll notice we have this par highlighted here. This is our first monadic combinator that we're seeing. It essentially means evaluate the two arguments at the same time in parallel. We use this to modelize OCaml's undefined order of evaluation, right? We're over-approximating here. The second thing I want you to notice is because we have an untyped semantics, we have this dynamic type check as clo that makes sure that evaluating the first argument actually returns a closure. Finally, the keen-eyed amongst you might notice that the last call to eval here, when we're actually evaluating the function body, is not permitted by rock. This is because it's not structurally decreasing. This is a non-terminating function. So in practice, we actually have a monadic combinator to give us the effect of potentially diverging recursive calls to eval. We call this please eval. So that's kind of the structure. Now, I mentioned at the beginning that we'll be focusing in on effect handlers during this talk. So let's see what that looks like in OCaml. As of 5.2, I believe, we have this nice syntax for installing effect handlers in OCaml. Performing an effect is just perform, and then installing the handler is adding this effect branch into a pattern match. So this match is saying evaluate the expression E, and then any effect that this generates is going to get caught in the third branch here, giving us access to the continuation K, which we can then resume when trying to handle the effect. At the level of our interpreter, I hope to convince you that this is actually very straightforward. Performing an effect is just calling another combinator, and handling, or rather installing a handler, is, again, just another combinator. I'd like you to pay particular attention to the right-hand side of the combinator, of the handle combinator here, where we're inspecting the outcome of the scrutiny E. We have this O, which stands for computational outcome. We expect in this function to be handling things that are either returned values, thrown exceptions, or performed effects. And then this eval branch's auxiliary function handles the actual pattern matching and tells us in which branch we want to go. Once we've matched on an effect and we're handling it, we potentially want to resume the computation, resume the continuation. In OCaml, the two keywords for that are continue, to continue a computation with a value, and discontinue in case you want to throw an exception at the point where the effect was performed. We use the same combinator for these two, resume. You'll notice here it takes a different type, outcome 2, where we're looking at potentially just returns and exceptions. So the reason I'm showing you this is I think it's pretty transparent. We've got this nice one-to-one correspondence between what we expect the semantics to be, and as long as we trust the combinators to be implemented correctly, this is very clean, very implementable, very maintainable, very scalable. So that's the top level. Of course, there's the bottom underneath. We actually need to implement these combinators. And to do this, we'll have a quick look at this monad. I hope to convince you it's also not too complicated. And we'll do that by desugaring the combinators that we've seen so far. Most combinators follow the same rough shape, which is this stop constructor, some code indicating which effect we're doing, some arguments, and then this ID2 here is just a trivial continuation for the stop. It's just an identity function injecting from outcomes to micro. In practice, this is actually just the Frege monad, right? They use different names in their paper, but we have this parameterized stop, which allows us to do arbitrary effects. And then in our computation trees, ret ends up being a leaf. Now, this is not all we need. We need more. We need more than just the Frege monad. And what I'll introduce next are more structural constructors. So the par and the handle desugar also very nicely into constructors. It's not much more complicated. But you'll notice these things carry microcomputations in their arguments, right? The par has 2 microcomputations that it holds in stasis. The handle has 1 microcomputation as well. So these are why these kind of don't quite fit in the framework of the Frege monad. And this is almost it, right? We add a few more types of leaves to model exceptions and undefined behavior. And that's actually a whole set of constructors for the monad. Again, this is quite short, quite maintainable, and quite concise, we find. So what's the story so far? We have this interpreter that relies on these effects provided by the monad, but we haven't actually defined how the effects behave yet. So far, they're just pieces of syntax, they're inert. And so I mentioned at the very beginning that we had a hybrid approach to our semantics, right? I said something denotational and stepping. So what we do is we add a stepping relation to this. But we don't add it at the level of the syntax, as you'd usually see in something like some Iris papers. What we do is we do it at the level of the micro-constructors, of these 6 constructors that we've seen. So we have this stepping relation on configurations of a computation and a store. And as an example, if we look at that please eval we saw earlier, we get this rule. If we clean up the continuation stuff here, look at a nice rule where we give it just the trivial continuation, you'll see that the combinator please eval in 1 step steps to the actual eval function. And this kind of open recursion we got is from this paper by McBride. It's well studied in principle. And it works well. Divergent calls are just an infinite chain of small steps. So that's for please eval. For effect handlers, we also have stepping rules, right? So a delimited handler here has this basic rule that says I can step under a handle. And what's more interesting is what happens once the computation under the handle has finished, right? What happens when we want to actually process the outcome of the computation? So 3 rules here, ret and throw are identical. We just pass on the value to the function that handles the pattern matching for us. But something funny happens for the perform here. So the perform itself is as we saw a bit earlier, just a stop code. But you'll see we're allocating something in the heap here. We're taking the continuation from the stop, and we're allocating it at a new location L. In fact, a heap is not only a map from location to values, but also a map from locations to either a continuation or the shot symbol. There's 2 reasons for this. The first is it's actually required in order to get the types to go through. If you don't do this indirection, you end up with a negative occurrence of micro in a type somewhere. So this is the hard constraint. And the second is that OCaml has one-shot continuations. Continuations can only be resumed once. And we need some way to keep track of which continuations have been resumed and which haven't. And we can see that with the rule for resuming. Here, the rule for resuming is if I want to resume some continuation that's been stored at a location L, then I read into the store, find the actual continuation that was stored there, actually compute it, apply the outcome I'm trying to resume, and I update the store to mark it as used. And kind of dually, if I try and resume a continuation that's already been used, then I just crash, undefined behavior. So again, I hope to convince you that there wasn't much complexity in the rules we've seen so far. Non-local control is not necessarily an easy thing to model, but this was very succinct and very close to what's actually in our ROC development. And that's kind of it for the semantics. We've got this nice hybrid approach. And on top of this, we will be building program logics. So you'll see I have another pyramid here, and there's a reason for that. It's because the architecture of the program logics actually follows the architecture of the semantics. When we build our program logics, we first build a bottom layer at the level of the micromonad. And then on top of that, we end up building a layer of program logics at the level of the surface syntax. Now, the cool thing is we don't have this API anymore. We're just using the reasoning rules of the monadic syntax in the proofs of the reasoning rules at the surface syntax. But once you've done that, you can stay in that top level, which means users never actually have to go back down into the bottom layer. They can stay at this nice level where they're just reasoning about pieces of OCaml syntax. They're reasoning about expressions. They don't have to know the implementation details of the monad. Now, you'll notice it's logics with an S here. And you'll also notice this pyramid is shaded. And that's because we have two. We have one pure program logic for pure programs. These are roughly programs that can step without having access to the store. And for that, we have a weakest precondition style judgment that says that says M, the computation terminates, and if it is a value, then it satisfies phi, and if it is an exception, then it satisfies zeta. And so the kind of rules you would expect is, okay, at the bottom level, we're reasoning about things like please eval, and then at the top level, we're reasoning about things like evaluations of expressions and pattern matching. And this is kind of a discovery that we made along the way, is that when you want to actually verify programs in this style, you end up having kind of a whole bunch of rules for each auxiliary function in the definitional interpreter, like eval and eval branches. And these end up being kind of their own judgments, which was kind of an interesting thing. And so you end up having one judgment per kind of syntactic construct in the language. And this works well. In the case of pure, it's very automatable, right? These things don't have side effects, so often you can kind of reason on them almost automatically. On the flip side, we have an iris-style weakest precondition that we call impure. You'll notice there's an extra parameter here. In fact, this impure is exactly the effectful weakest precondition from this previous work for reasoning about effect handlers. So I won't go into detail about how this is implemented or what the reasoning rules are. All you need to know is it's the same, lifted from that paper to a new environment. So now we're in iris, so our post conditions are in iprop instead of prop. But the constructions are very much the same, right? We still have this bottom level where we're reasoning about things like handling effects, right? Micromonad. And then at the top level, we're back to reasoning about things at the surface syntax. So things like eval A to E. This deep handler judgment is also from the separation logic for effect handlers paper. And we actually end up with the same reasoning rules as that paper as well, which was quite nice to see. Finally, the two program logics do form a whole. They can interact. We have this nice rule that says, if I can prove purely that some computation has some postconditions, then I can use that fact in impure proofs. So at any point in an impure proof, you can kind of step down into the pure world and maybe use some automation there to complete some easy branches of your program. Finally, just to wrap things up, we have a validation step for our semantics. We have this interpreter defined in rock, and we have this stepping relation. We can actually execute this by using rock's certified extraction to OCaml, right? The interpreter can be directly extracted into an OCaml function, and then we can simply use the stepping relation by iteratively applying it. And what this allows us to do is we can then test for inclusion of the behaviors that are actually displayed by the OCaml compiler against the behaviors that are allowed by our semantics. And this is all parameterized in order of evaluation, so we can try and mimic the order of evaluation of the compiler if we want to restrain our subset of tests, or we can just model our non-deterministic order of evaluation if we want. So to conclude, this is the kind of the full picture. What we have so far is a very, very large subset of sequential OCaml, including effect handlers. Current work in progress is happening on concurrency. That's the next step. And then finally, I mentioned at the very beginning that so far we have an untyped semantics, which is fine, except when you want to start thinking about modules, because suddenly you need to know about the module signatures and which fields to import and which ones not. So we need some reification of the types, which I think we'll get to as soon as we finish concurrency. Thank you. There are 2 microphones. Tell me the question, I'll repeat it.
Is this okay? So thank you for the talk. You showed your 2 logics nicely. I was curious, does the pure logic actually exist in the sense of, is there a real definition of it? Or could you just have it as derived rules for the impure logic? I mean, you showed this embedding. It seems to me that it means that every pure logical proof that you have, it becomes an impure logical proof. Why is it, like, is it real, and if so, why?
It does exist, so it's its own weakest precondition. There's its own stepping relation that we relate to the impure stepping relation. That's how we get that rule that the 2 commute, in a sense. As to why we did it that way instead of just kind of hiding it within the impure reasoning rule is that these kind of abstraction barriers are very hard to maintain in proof assistance. It's very easy to slip, and suddenly you're exposing impure goals in what you thought were pure goals. So it would definitely be an approach. I'm not sure how well confined that would keep it within the proof system.
Okay, so then as a short follow-up, would you say that it's really more of a question of engineering? I mean, with more experience in being able to sort of wrangle the theorem prover, I guess you would go down back to 1 logic.
Yes, I think so.
Yeah. All right, thank you.
I mean, there's also the fact that it is a total logic as compared to the Iris one, which is partial. So if you're interested in proving termination of your programs, then you need to go into the pure thing. But you could also say, I can have a total logic in Iris, so that's a debatable point. Yes?
So hi, I'm Cesar. I'm from MPASP. I have 2 questions. So I think the first is related to the previous question. So you need impure to talk about system calls, or why do you need this impure?
So only the system calls that depend on state. So as we saw, please eval is a system call that independently of state will reduce to eval. So that's pure. And something like handling an effect depends on state because you need to read the state. So that would be an impure.
Okay. And then my second question is, did you try to verify an OCaml program using this, and how easy it is to use your work?
Right. So we don't have a big case study. We do re-implement the case studies of the effect handlers paper, and we do have some small examples that we were working on specifically for the pure sublogic. It's not any easier or harder than any other Hoare logic, is my impression. We end up with syntax-directed rules that you just apply as lemmas, and then you can add a thin layer of automation over that, but it's still deductive verification. Thank you.
Hi, Simon Spice from Jane Street. Have you thought about how extensible the system is? Like, say, if you were to add a bunch more features to a language like OCaml, how would that change this semantics?
So we've thought about the ability to extend it in the sense that we've thought about all the existing features of OCaml that we might want in the model, and we've tried to make sure that we'll be able to do those. In terms of extensions, there are essentially 2 kinds, right? There's adding more effects to kind of just the freer monad. Things like adding more stop codes, that's fairly straightforward and easy. And then there's, if you wanted to add more difficult things, if you wanted to start reasoning about locality, for example, you'd have to re-engineer a lot of things, and that's really not as clear.
Okay. Thanks. Oh, very nice talk. I think I forgot to say that.
Thank you. Let's thank Remy again. Okay. And now we will hear Rutger talk about the semantics of NICs.
Right, I hope I'm audible. Okay, so I'd like to start with a proposition, namely that having the formal semantics for a programming language is quite awesome, and because we can do multiple things with this kind of stuff. Because we can be extremely precise about what the language actually means. So we can do stuff like creating program logics, we can verify compilers if we have multiple implementations of the same language. We can make sure they agree, or stuff like static analysis tools. We can verify that they are correct. Now if we give a kind of executable semantics, then if we have some kind of a test suite for the language, or we want to test this on some example programs, then this becomes quite easy. Or if we have a reference interpreter, then we can also do that kind of stuff. Now if we have a proof assistant that we actually make use of to mechanize the semantics, then we can also do stuff like verifying, for example, this reference interpreter. So we can reuse this very easily. Now this is kind of stuff has been done before, so think of CompSert, this kind of stuff. Today we won't be looking at any common language like C, we'll be looking at a kind of weird language, NICs. And we'll get to why in just a second. We'll be discussing two kinds of semantics because they're good for different kinds of things. So substitution-based operational semantics, that's nice for creating stuff like program logics. It's concise, readable, but quite inefficient. You wouldn't want to actually execute any kind of a program with this because your terms tend to blow up a bit. So environment-based interpreters are better for this, they're nice for testing, and they're relatively efficient, but they're not nice for reasoning with. So we'll be discussing these two perspectives today. So first we'll talk about what NICs even is for the ones that don't know. Then we'll be discussing why NICs, and then about how we went about creating these kinds of semantics. So what is NICs? It's primarily a package manager that has this kind of purely functional aspect to it. So whenever you have a package, you kind of pin all of the dependencies, and the idea is that the build process is sufficiently isolated that you always get the same kind of result. Ideally, you get this kind of binary reproducibility where you always get exactly the same output. And now NICs is a distribution that's based on the package manager, where you can have declarative kind of configuration, and at the heart of all of this is the NICs expression language. And you can see here on the side that you have an example package. This is for the own tracks recorder, and this is what the NICs expression language looks like. So this is what we'll be discussing today. So I want to just give a quick overview of what this language looks like. It's functional, lazy, and untyped, so in some sense it's a bit similar to Haskell, just without the types and a bit different. So lambda abstractions, they have this syntax. That's a good one to remember. You'll be seeing it a lot. And NICs is lazy, so for example, we have big omega there, but since it's not used after the let, this program doesn't actually loop. Now let bindings are also mutually recursive, so we can define the Fibonacci function just like that. Now there's also attribute sets in NICs, and these appear everywhere. So you could also see them in an example before. And these also allow recursivity, mutual recursion between the different bindings of the attribute set. So for example, the Fibonacci function can also be defined inside of a recursive attribute set, and then we can call it by selecting it from the attribute set. So that's just like a JSON dictionary, but with code. Now there's more kind of interesting or weirdish features of attribute sets. So if you add an underscore functor attribute, then all of a sudden the attribute set itself can be called. And then the first argument to this underscore functor thing, when it gets called, is the attribute set itself. So that's how this again turns into Fibonacci function. There's more interesting stuff. So NICs has dynamic binding. This is something that we'll be focusing on the next few slides. And then there's also different evaluation strategies using sec and deepsec. So I just want to have you think about the following programs, about whether they are well scoped or not. So NICs has this with construct. It takes an attribute set, and then it makes all of those available in the second argument to the with construct after the semicolon. So in this case, we see that x and y are defined in the attribute set, so clearly they will be available on the right-hand side. So this program is indeed well scoped. But for example, we can also kind of extract this attribute set and then bind it to some variable and then use that with the with. But this is, of course, still well scoped. That seems just fine. But note that this can be any expression. With is not syntactic sugar. So if we have some kind of a let binding that calls some function that generates some, presumably an attribute set, then of course it's not clear anymore whether x and y will be bound. So we'll have to say, maybe. We don't know if this program is closed. Now, shadowing behavior in Nix is also a bit weird. So for example, well, let works just like you would expect it to. That returns 12. But if we have, well, if we have 2 times width, then things get a little bit tricky, but this still works the way you would expect it to. So that's also good. But if you have a let first and then a width afterwards, then all of a sudden you'll notice that let takes priority over width. This is a bit weird. Now the other way around, this still works the way that you would expect it to. Now if you take this in the context of the Nix package manager, then this makes some sense, but I won't go into detail about why. Now, one more thing that I want to mention about the semantics of Nix is these different evaluation strategies. So normally if we have big omega, this term that has no normal form, then if this is just in the let binding that's unused, then this of course still returns through this program. Now if we have sec, then the first argument gets evaluated to weak hat normal form before the second argument is returned, but of course this loops because big omega loops. But if we put it inside of a list, then again, Nix is lazy, so the elements of the list don't get evaluated, so this just returns true. Now with deepsec, this kind of evaluation is done recursively, so this loops, because omega loops. But if we have 2 attributes, x and y, well, in this case, y should crash, because this is an invalid application. So the question is kind of, what does this program do? Does it crash, or does it loop? And in this case, well, it depends. Because in the case of Nix, it does not by default evaluate stuff on an alphabetical order. This kind of depends on the order that the different names basically like appeared first to the interpreter. So this is weird. But anyway, that's a nice challenge to formalize. There's one more reason why it makes sense to give a formal semantics for Nix. So this has been kind of done before by the original author of Nix, Ilko Dolstra. He has written down some formal semantics, but these are a bit lacking, so they are not tested, not complete, and such. And there's also a case where the semantics for the with statement are not very precisely specified, which makes the substitution kind of go wrong. So this is done naively, but that causes the shadowing for with to not work properly. Now, as of 2025, there's also a decent selection of Nix implementations that you can choose from, but I'm not aware of any common specification for the language. So it might be time for something like this. Now that we've seen all of these peculiarities with shadowing, this with construct, we might be wondering, okay, so how do we even start to define a substitution-based operational semantics? Now you might say, okay, just use something like the Brown indices or whatever, but this doesn't work for Nix because names are relevant, as we saw before. So we wouldn't know what the Brown indices to assign to x and y here. So you might say, well, just use strings, but strings are really annoying because you have to do stuff like alpha conversion, and we want to do stuff in rock, and alpha conversion in rock is hell. So we want to do something else. And what we came up with is some form of deferred substitution, which is still pretty concise. You don't really get capture problems. And even when you reduce open programs, this still works the way you would expect it to, so we don't get this kind of weird behavior. And this scales to the with construct in Nix, also dynamic variable lookup, and also constructs like eval, even though Nix doesn't have those. Now just to illustrate, I want to quickly discuss the call by name lambda calculus and show you that when we handle an open program in here, then this goes wrong. So for example, you see that y is unbound at the top level here. We reduce by 1 step, and then all of a sudden it becomes bound because it's substituted into this lambda abstraction. And if we take one more step, we get this string a, but that's really not the result we want. So of course we can do alpha conversion, but again, like I mentioned, alpha conversion is really annoying. So what we do is the following. You might be familiar with explicit substitution. We can do this in a kind of way that we still preserve names, and what we do is we kind of push through these explicit substitutions and we just reify them at the variable level. So there's this association list of variable names to expressions that we associate with the variable name. But you might say, okay, but this is dumb. We already know the variable name. Why would you associate all of the possible substitutions with this? And I would say, well, you're right about that. Can be simpler. So we can do one of two things, right? So we can just say that there's an optional substitution that we associate with a variable. So if there's none, then this is just a plain variable, and we'll often just write it x instead of x none. Or there's this deferred substitution e that we associate with the variable, and at the point that this variable then appears at the top level, so that when there's no binders around it anymore, then we can reduce this to the deferred substitution itself. We can also choose to generalize instead and have the variable names or even the binder names for the lambda abstractions computed dynamically, but if you want to know more about this, I would suggest you to read the paper. There's also one more strategy that I would just like to honorably mention. This is by Ben Lippmeyer. He revised the substitution at the lambda abstraction level, but it's not clear to us if this scales to the next features that we want to implement in our operational semantics. So just one more time to make this a bit clear how this works. If we have this deferred substitution associated to a variable at the top level, then we can reduce this to the deferred substitution itself. And all of these rules, we only reapply them at the top level, which makes sure that we don't actually get any kind of capture problems. And important to note is that the substitution function always allows this deferred substitution to be overwritten. This is a pretty core piece of this and why it actually works. So let's look at this counterexample from just before again and use deferred substitutions instead. So you see this y here, you should read that as y none.
Sorry, can you?
That seems to be working. Okay. I hope I'm audible again. Okay, so guess you've had some time to read this now, and this should be pretty obvious to you at this point. When we reduce this, then we don't substitute inside of the deferred substitution, so we don't actually get capture. So when we reduce here, then we get y as a result, which is exactly what we want, because we do not want this program to actually evaluate correctly, or we don't want it to evaluate to a value at least. So this is a better result. Now we do multiple things in our paper. So we have multiple interpreters, and for all of these interpreters, we have this kind of a lemma. So the interpreter that we define is sounding complete with regard to the operational semantics with deferred substitutions for terminating programs, faulty programs, and diverging programs. And this all holds for open terms. You might also want to note that for the interpreter, there's this environment associated with this. That's the empty set in all of these cases, because we are considering normal programs that are, yeah. Okay, so now we have seen all of this kind of stuff, and you might be wondering, how does this all transfer to Nix? Because Nix has this weird shadowing stuff. You've talked about the closed terms, but not about the weird shadowing stuff that's going on with the width. So we do this by extending the deferred substitutions a little bit and basically assigning a kind of binding kind with the deferred substitution. So this means, so we adjust the substitution function so that basically whenever we want to substitute for a variable again, and it has a stronger kind, so the abs kind, then we can override it. But if it has the width kind, then it is not overwritten. So you can also kind of see this below, that we have this abstraction kind. That's what's generated by the let, because it has the same strength as a lambda abstraction that's associated with the substitution. So we get the kind of shadowing behavior that we would expect. Now, just to intimidate you a little bit, this is the entire grammar of our core Nix language. So some interesting things to highlight are the following. This is how we define recursive, or how we define attribute sets. All of the attributes have a separate recursivity instead of the attribute set as a whole, because this is much more convenient. Dosser also does this in his earlier semantics. We have pattern matching lambdas. If you want to know what these are, I have a backup slide for perhaps a question. Then there's the sequencing construct, so deep sec and just normal shallow sec. And we also support IEEE floating point numbers using the flock library for rock. Now all of this, we have a front end for this. So there's the interpreter that we've written and verified in rock. And it takes this kind of core Nix expression and translates it to a value. And we have an OCaml front end, which basically parses Nix code, elaborates it to the score language, and then gives this result. So we pass a decent amount of language tests, although definitely not all of them apply. A decent amount of language tests are also simply not interesting to us because we don't consider the package management aspect of Nix, or we don't really care about XML encoding and this kind of stuff, which Nix does support. Now we don't agree on all tests. There's still some which we don't pass because our interpreter is, as I mentioned, call by name, but Nix is lazy. So we can't detect cycles, for example, in some cases. So just to conclude, what we've contributed are the following. We give a form of deferred substitutions that also scales to dynamic and scripting languages like Nix. We prove the soundness and completeness of environment-based interpreters with regard to these kinds of deferred substitution-based operational semantics. And we give the most comprehensive semantics of Nix to date, as far as we know, which is evaluated on the Nix language tests. That's it. Thank you very much.
I will start. So, like, given the title of the session about separation logic, do you plan to have like a logic for Nix, or?
So we have defined a small program logic for this, a weakest precondition-based logic, and we've done some simple proofs in Rock for this as well. But we didn't create any kind of tactic support, so this was still quite cumbersome. But it is possible to do this kind of stuff, yeah.
So I was curious about this comment you made at the end. Do you foresee any issues with combining laziness with the deferred substitutions that you've shown so far? Or fundamentally, is there another reason why your calculus is called by name? There are lazy calculi out there.
I don't think that there should necessarily be any issues, or I can't come up with any immediately. But in general, defining a lazy operational semantics is a bit annoying. So defining a lazy interpreter, I think, is quite a bit easier. As far as I know, there's currently a student of Robert who's working on this. But I, in general, don't know if it makes that much sense. Although I guess if you really want to match the Nix interpreter as it exists today in your operational semantics, you would have to define it in a kind of lazy way. Because Nix does like weird pointer equality kind of stuff when comparing stuff. So if you want to get this exactly right, or at least if you would take the official Nix interpreter to be like the semantics, then yeah, you would have to, I guess, do a lazy operational semantics. So it might be quite tricky, yeah.
Yeah, thank you.
Hi, thanks for the talk. It seems like the with statement caused you a lot of trouble, and I think other Nix alternatives out there have had similar issues, like Nickel. Do you think the language really needs this feature, or is it just to be interoperable that you're, yeah?
I don't necessarily want to rate the features of Nix, but with is definitely a bit weird. And I believe that Nickel indeed also doesn't have this feature, but somehow this still seems to be fine. I believe that there's other ways to get similar kinds of constructs which have similar nice properties, so you can like bring all packages into scope, so you don't have to prefix these with packages dot or whatever. So I think that there might be nicer solutions than with, because for example, JavaScript also has with, but not strict JavaScript, which everyone is supposed to use now. So it's also kind of been banished from there. So yeah.
Right. Thanks.
Thank you for the talk. I think this is really cool. I guess one of the interesting things about Nix is how much of like the tooling in the ecosystem is in the language itself, and so even just verifying these core aspects of the language is useful. But at the end of the day, because Nix is still predominantly used as a build system and everything comes down to the derivations. And I know you said you weren't interested in doing that because you were interested in like these aspects of the language. But what do you think the approach would be for wanting to have like a complete verification of Nix, including the build system?
That's a good question, and I haven't given too much thought to this yet. But I think it would get very complicated very quickly, or you would have to I guess you would need some kind of a way to like interface with the outside world, because Nix has stuff where you can, like, for example, I don't know, fetch a Git repository or fetch some kind. You have like these built-in functions like fetch URL.
Yeah, it has a lot of built-ins that have I/O, like not pleasant I/O, basically.
Right. So there's like some I/O going on. Although I guess in Nix you always indicate hashes. So then this is still, in a way, always going to give you the same result, or at least as long as it like successfully executes, then it's going to give you the same result. So that's at least one nice aspect of this. But I'm not sure what the value is in defining the semantics of the build system itself. Yeah.
Okay, thank you.
Maybe it could give you an idea. Like there was a project to kind of do like static analysis on the Debian scripts, like install scripts, and then like model checking to check that the scripts would install properly and so on. So like there is previous work on build, install stuff. Yes, I guess like what are your next steps in general for this?
For now, there's no plans for next steps. This is not part of a PhD or something. I'm a master's student, so there's no planned future work, but who knows what the future will bring.
Okay, thank you. So let's thank the speaker again. Okay, and now Marcos will tell us how to verify graph algorithms using an algebraic approach.
Okay, so thank you very much for the introduction. This talk is going to be about separation logic and its problems with graphs. So separation logic is a method for verifying heap manipulated programs. Its main characteristic is reasoning about heap decomposition. This is achieved via its main connective, the separating conjunction, which formally states that P separating conjunction Q holds of a heap H if it can be decomposed into two disjoint heaps H1 and H2 such that P holds for one and Q holds for the other. The main specification pattern of separation logic involves describing the heap layout by predicates. So for example, we could define a list predicates such that we could specify that the heap H store a linked list between pointers I and j, for example. We will refer to these kind of predicates that describe the heap and other heap-related concepts as spatial. So these spatial predicates are often parameterized with non-spatial data. By non-spatial, we mean abstract mathematical structures. So for example, we could extend our list predicate with as non-spatial argument a mathematical sequence. This way, what we will achieve is, in the verification process, abstract away from the heap and reason instead about the mathematical sequence and its properties. In practice, this list predicate is defined inductively on alpha using star and other separation logic primitives, which will enable us to decompose this structure in the heap. So the purpose of this spatial decomposition is local reasoning, which is achieved with the help of the inference rule of frame, which involves disregarding the part of the heap that the program doesn't touch. This way, localizing reasoning to the heap that we really want to reason about. So if we're given a program that mutates the head of a list so that its contents change to point to B, we can actually decompose the list, disregard the part that we don't care about, apply the mutation, and then reattach the pieces afterwards. So an important observation that is not often made explicit is the fact that spatial decomposition induces non-spatial decomposition. What we mean by this is that in order to decompose the list in the heap, we first need to decompose the mathematical sequence via sequence concatenation. So this is trivial in the case of lists because of concatenation. However, for graphs, this is not the case because there's not such a notion of decomposition. So a popular potential fix was proposed in an early work of separation logic in 2001 by Young, where in a seminal proof of a short-weight graph marking algorithm, he avoids graphs altogether. And he does this by, instead of relating the heap to the mathematical graph gamma, he relates it to multiple graph abstractions that approximate the structure and that are parameterized by structures that do actually decompose, such as sequences and trees. The problem with this is that these multiple graph abstractions are very tedious to synchronize with each other and with the heap, which amounts for most of the complexity of Young's proof. Furthermore, and most importantly for us, because you don't have the graph at the non-spatial level, you cannot neither construct nor use graph libraries. So our contributions begin by observing that graphs do generalize to support decomposition if we define them as partial commutative monoids. However, this is not enough. There will be cases where we'll need more algebra to localize the proofs. For that, we will introduce PCM morphisms, which will play an analog role to framing, but at the non-spatial level. This will enable us to localize reasoning even about what they are usually referred to as global properties. This will shift most of the reasoning from the spatial heap level to the mathematical non-spatial level, where graph libraries can be constructed and reused. This will lead to new and concise proofs of both benchmarks of short weight and union find. So let's now move on to see how we define graphs as partial commutative monoids. So to the question how to decompose a graph, we attempt a pictorial argument. So we have here the following graph with the following divide. So we argue that the way to decompose it is as follows. But however, this has the problem that one of the components is not strictly a graph because there are dangling edges which are not usually considered in the classical definition of graphs. So from this observation, we conclude that we actually need graphs with dangling edges in order to make them decompose. And these are precisely what partial graphs are. We define formally partial graphs as finite maps from nodes to a pair, with the first element being the contents or marking of the node, and the second element being its adjacency list. Notice that because we allow for dangling edges, some of the nodes in the adjacency list may not be themselves in the graph. So this is a single node graph that which can be represented as A maps to the contents X and the adjacency list ABC. So partial graphs decompose with the join operation, which is defined as plain union if the nodes are disjoint and undefined otherwise. This operation is partial, commutative, and associative. And with the empty graph as unit, it conforms a partial commutative monoid. With this notion of composition, partial graphs compose and decompose trivially. The second notion that we introduce is that of PCM morphism. We will define it as a function f from A to B that preserves PCM structure. So we will emphasize here the second equation, which corresponds to the distributivity of the function f over the graph. This will be important. Some examples of graph morphisms are the nodes of the graph, the sinks or the nodes with incoming edges, any kind of filtering about the contents of the nodes, or any kind of mapping a function throughout the graph. all of these and many more are examples of graph morphisms. Each will have its corresponding distributivity equation. So as for non-morphisms, these will correspond to properties that are often referred to as global. This is the case because these are exactly the properties that, when decomposed, are not preserved. It is possible the case that they are not computable from its individual parts. So an example of a non-morphism is the property of a graph being closed, meaning that it has no dangling edges. As we saw in the example of the decomposition of the graph, we began with a graph which was closed. When decomposing it, one of the subcomponents violated the property of being closed. Okay, so how do morphisms localize proofs? We begin by showing some analogies with the frame rule. So the same way the frame rule decomposes the heap by using the separating conjunction, morphism will decompose the graph, but in terms of the join operator. The same way framing localizes to the heap that holds of P, morphism will localize the subgraph gamma 1. And the same way framing removes from the specification the heap that holds of R, morphism will factor out gamma 2. As for the differences, there's one advantage of morphisms over the frame rule, which is that it is possible to rewrite inside any arbitrary context, while the traditional frame rule applies mainly at the top level of a specification. The second and biggest difference is the level at which each of these patterns of localization actually operate. So we have the frame rule, which applies at the spatial level of heaps and programs, whereas morphisms apply at the non-spatial mathematical level. The conclusion from this comparison is that we actually need both. So let's now see in verification. So we need to prove the following lemma about the preservation of closure. So we suppose we have a graph gamma such that x is in the nodes with two outgoing edges to, let's say, xl and xr. We note that the graph is closed and that y is also in between the nodes. Now let gamma prime be the result of redirecting the left edge of x in gamma to point to y. The lemma says that this resulting graph is closed as well. So I want to point out two things. First of all, that because of the PCM morphism, we have that the rest of gamma, which is not x, is actually unaltered. And second, that what we are asked to prove is actually a global invariant because, as we saw before, it's not a morphism and it does not distribute. So how do we proceed? So the key idea is that even though the property is not a morphism and it does not distribute, we can very often define it in terms of morphisms, and in that case, we will find the distributivity and the locality deeper inside the property. So we do just that, and we define it in terms of sinks and nodes, which we saw were examples of morphisms. So by saying sinks of gamma prime are contained in the nodes of gamma prime, we are saying that there are no dangling edges. So we proceed by equational reasoning, and we start from sinks of gamma prime, and we want to get that this is contained in the nodes of gamma prime. So we begin by rewriting by the definition of gamma prime. We then want to distribute so that we factor out the rest of gamma, which is not x. We are going to exaggerate this distributivity to make clear our point. And from now on, we will be reasoning about the single node graph x pointing to y and xr. So we begin by rewriting by the definition of sinks, which gives us y xr. Then by simple set inclusion, we get that this is contained in y union xl xr. And at this point, we again rewrite by sinks. And at this point, we can already rejoin the factored out graph by the distributivity equation, but the other way. this way we get the sinks of gamma, which by assumption we know are contained in the node of gamma, and we also know that Y is in nodes of gamma, so all is contained in the nodes of gamma. Finally, the last step is to prove that the nodes of gamma are contained in the nodes of gamma prime, which follows more or less the same pattern, so we will not get into the details. So as you see, we have been able to factor out the part of the graph that has not been altered and reason locally about this single node graph. So in verification in general, what we want to do is define the key properties of the algorithm in terms of morphism so that this pattern can actually apply. And this is what we do precisely for the case of short-weight graph marking algorithm. This algorithm marks reachable nodes from a given route, and the interesting part is that it encodes the stack for backtracking not as a separate structure, but by encoding the stack by reversing the edges of the graph itself during the traversal. So it achieves this with two auxiliary variables P and T, and 4 different node markings, so unmarked, left marked, right marked, and fully marked. The left and right nodes will encode the nodes that are part of the recursion stack. We will highlight those in red, and so let's see a partial execution. So we begin from the root, and we proceed depth first search. Notice how in the process we are swinging the edges so that the backtracking information is always maintained, all while marking the nodes. So in the end, an intricate thing to prove as a postcondition is that all the edges are restored back to their initial position. For this, we need a loop invariant that relates current graph, initial graph, and the stack. Remember, we want to encode this as a morphism in order to reason locally about it. So the first observation that we make is that the key transformation of short weight, that of reversing the edges, is node local. So it's expressible as a node local higher order function that branches on the marking. Once we have this function, in order to state that all the edges are restored, we apply it to traverse the stack. We iterate it over the whole graph by mapping it through gamma, and we finally equate it to the initial graph to relate to the starting edges. And because we know that mapping a function is a morphism, we have encoded this complex invariant in terms of morphisms, which will allow us to apply this pattern of localization. So this is the full invariant of short weight. Of course, we are not going to get into the details of it. However, I want to point out that all of these circled concepts are actually morphisms. And a similar situation happens in union find. So as conclusions, we have generalized the notion of graphs so that they support decomposition. And we have introduced morphisms as the non-spatial analog of framing. This way unlocking a new pattern of localization that enables local reasoning also about global properties such as closed and the loop invariant. And this has shifted the amount of reasoning from the spatial level to the non-spatial level where libraries can be built and reused, which result in very concise mechanized proofs. So more precisely, the proof of short weight takes 110 lines of rock and union find 49. Of course, all of this being supported by a general graph library of reusable lemmas. So this is the artifact, and that's it. So thank you very much.
So like which separation logic did you use in ROC? And is it like agnostic to it, or?
Yeah, so it's a standard separation logic from early papers on, yeah.
Which one?
Yeah, from 2001, Peter and Hearn and company, yeah.
But like, do you think it would work on?
So
iris?
it's not. So in Rock we don't use iris. We use Hoare type theory, which is a type theory that that is used to reason about separation logic. Yeah. But but this method is general in the sense that if you have framing and separating conjunction, you can actually apply it and get the same results. So yeah.
Hey, thanks for the talk. So, I mean, I think it was a lot of fun. So the one thing that wasn't really clear to me is it's like, so like we say that sort of for this technique to work, we need to rephrase things about graphs in terms of these partial commutative monoids, right? But then it's like, once we rephrase them, how do we reuse a general graph library? Because a general graph library will be talking about stuff in terms of vertices and edges or whatever, right? So like, it's not clear to me. Like, do you need to write a specialized library for PCMs and how they relate to graphs, or like what? Like
right. No. So it's a general graph library where graphs are defined as PCMs.
Ah, okay.
So it's general in the sense that this definition and the spatial predicate of graphs can be applied to multiple algorithms.
Right.
So we've used it for short weight and union find, but any algorithm. Any graph algorithm can actually use the same predicate with the same definition of graphs.
Right. Okay. So then I guess that brings me to my second question, which is, So right. So like, if we think about, or like, I mean, in the example that you showed where you defined this closed predicate, right? Yeah. It was like, like you needed some amount of cleverness in order to redefine it in something that does actually like distribute correctly, right? Like in terms of the, So I mean, I guess my question is like, I don't know, is there like a textbook already that tells me when I redefine things in terms of PCMs, how to take all the concepts that I'd find in like undergrad graph theory in a way that works well and distributes nicely? Or is it that like you had to come up with the right definitions for your particular thing, and there's still open research to be done on coming up with definitions that work well with
Yes, there's definitely not a textbook of how to define things in terms of morphisms. So that's, I think, the main thing that you have to reason about when verifying following this approach. That so you have these properties that changes throughout depending on your algorithm. And you have to figure out how to actually define it in terms of morphisms. Yeah.
Okay, thank you. I'd be interested to chat a bit more later about this library design. Yeah.
Yeah. Thank you.
Hi. So I'm confused about this distinction you have between the sort of pure logic and then the separation logic. So, but do I understand correctly that the pure logic also?
No. So at the spatial level that we call it, it's the heap. So you have pointers and maps to and the separating conjunctions. And then what the non-spatial level is where mathematical structures live. So you can the sequence in the case of list and the graphs in our case. So.
And that is also a separation logic.
It's part of it, yes. It's like a different level of reasoning about it, yeah.
Okay, so it's like you have two separation logics with different logical resources, no?
No, so it's one separation logic, but you parameterize these predicates that specifies the heap in terms of mathematical structures. And these mathematical structures can be anything that you can define in pure mathematics.
So you have two instances of a single separation logic? No.
Not exactly, no.
I think I should read the paper, maybe.
Maybe, yeah, and I can explain further if, yeah.
Okay. Yeah, thank you.
Yeah.
Hi, thank you for the great talk. So I'm wondering if you consider a tree and an invariant on a tree that also like talks about the heap resources, and if your tree invariant needs to, like for each node, if it needs to keep some information about all of its children, will your technique help to make reasoning like localized for each node?
Well, for trees, there is not so much problem as with graphs because, there has been work on trees that uses like traditional methods, and there hasn't been, or at least they haven't been explained that there were any problems with it. So, but of course, the same things about trying to specify your properties in terms of morphisms will as well apply. So I don't know in this which morphisms would apply in your specific case, but very often it is the case that you can actually do that. Yeah.
Right. Thank you.
Thank you. So let's thank the speaker again. Okay, and for the final talk of the day, of the session, Anders will tell us about how to reason about weak isolation levels using Iris.
Yeah, so hello everyone. So I'm here to present our paper, which is really about how you can verify transactional databases. So the databases that we consider, they're quite simple. They're key value stores, and they just have these two operations. So you can either read from a key, or you can write some value into your key. So you can write 1 into X. Now, databases, they run in very highly concurrent settings. So there could be thousands or tens of thousands of users wanting to access this database at the same time. And as we all know, then users of databases, they're very impatient people, so they don't like to wait around. And if they wait around too much, they become angry, and they become all red, as you see. So it's very important that our database is fast, that it has very high throughput. But at the same time, we must, of course, maintain the correctness guarantees of the database, so the guarantees that we are going to provide the users. Otherwise, everyone is just unsatisfied. So if we are in the business of implementing databases, we really have to balance these two things. So as much throughput as possible, and at the same time, it should be correct what we're doing. So most major databases, if not all databases, they provide transactions. And transactions, they are very hard to get right. And at the same time, they're really something which can slow you down and give you very low throughput. So this is what we focus on in this paper. Now, what is a transaction? Well, it's sort of a way to group individual database operations into these units that we can then reason about. So for clients to be able to group their operations into these units, we have to give them 2 additional operations. So now they also have a start operation and a commit operation. So as you see, to start a transaction, a client is going to say start, and then they can do as many reads and writes as they want. And then in the very end, when they are done, they can use the commit operation and commit all of their changes. Now, what transactions gives us, and the reason why we want them, is that instead of having guarantees for the individual operations, we can now have these guarantees at this unit, this grouping level. So we can talk about guarantees for transactions. And sometimes it can be the case that a transaction is just about to violate some guarantee of the database. So therefore, the database needs the ability to reject some transactions. So in practice, this means that the commit operation, it can actually fail. So it can be the case, a client is about to commit some transaction, and the database sees that this is not okay, so I'm going to fail you and tell you to try again later on, and then roll back your changes. Now, what are then some of the reasons why sometimes we have to fail these transactions? So that's because we are about to violate these guarantees. And there are some things we can always count on when using transactions. So there are 2 things which are like baseline guarantees. And these are that writes, they're applied atomically. So either no writes are applied, or all the writes of the transaction is applied. Then we also have this property that the transaction, it runs sequentially internally. Now, what does that mean? So it means you're reading your own writes. So for this transaction, when you're writing 1 to x, and you're just reading x thereafter, you always know that this is going to return 1. You see your own changes. So the things that I haven't told you about yet is what about all these non-local reads? What about the reads that you're doing from all the other potentially concurrent transactions? What are you actually allowed to see? And to talk about these, we have a bunch of isolation levels. So they state how isolated is your transaction from all of the other transactions. What can you actually see? So we can use these isolation levels to answer questions such as, can I execute my transaction as if I'm the only one in the world using this database? And it turns out that the answer to this question is actually sometimes yes. Sometimes you can imagine that you're the only one. So one of these isolation levels, often what we consider the strongest one, is called serializability. So under serializability, transactions, they execute 1 at a time. So in this example execution on the slide, these boxes are our transactions. So first we apply the writes of transaction 0, then we apply the writes of transaction 1 on top, and on top of that we apply transaction 2, and so on. Now, underneath this transaction, we have these arrows. So I call these read arrows. So it means, for instance, that transaction 1 is reading from transaction 0, and transaction 2 is reading from this snapshot created by first applying transaction 0 and then transaction 1. And what we get from serializability is that these read arrows, they are always perfectly aligned. So each transaction always sees the most recent snapshot. Now, the problem with this strong guarantee, and I was mentioning throughput before, it is that this can imply a lot of failed transactions. So all concurrent transactions, they are competing for being the next transaction in this line to be applied. So in the worst case, it can be that we have to fail 1, but the winning transaction of all our concurrent transactions. So this will really tank the throughput of our database. So we are quite lucky in that there are weaker guarantees, and we call these weak isolation levels. So many people have made the observation that not all use cases need strong isolation. In fact, if you create an application tomorrow and then you need a database and you find this database on your favorite cloud provider, then as default, it is not going to run strong isolation. It will run one of these weaker levels. And an example of one of the most popular levels is called snapshot isolation. So this is different from serializability in the sense that transactions, they read from snapshots of the database, and we call these starting snapshots. So they're the most recent snapshot at start time. Then at commit time, a transaction is allowed to commit only if it has no write conflict with any of the other concurrent transactions. So I have an example execution again. The first 2 transactions, 0 and 1, they're just like in serializability. The read arrow for transaction 1 is perfectly aligned. But then we have 2 concurrent transactions, transaction 2 and 3, and they share the same starting snapshot. Yet we allow them to commit because they don't touch any of the same keys. They don't have any write conflicts. So this is a way to get more throughput with this weaker guarantee. And to just drive this point home about the differences between some of these levels, let's just consider a small example. So say we are creating a banking application and we want to transfer this some amount from a source to a destination account. Then a code snippet for this could look like this. So first we start the transaction, and then we read the source balance out of the source account. And then we have to check whether there's actually enough funds in this account. And if that is the case, we can go ahead and subtract the amount out of the source account. And then we can also update the destination account by reading its balance and then adding this amount. Now, if we didn't have logs or transactions or any other safe concurrency mechanism, then we can imagine all sort of nasty executions with this example. So for instance, it could be that two clients, they're trying to transfer money to the same account, but one of these transfers is lost. The money is not put into the destination, but yet it is still taken from the source. So a property we would like to have is that we have at most one transfer per account at a time. And actually, both these levels that I have presented to you, they give us this guarantee. So I think for serializability, it's quite clear that because transactions, they indeed run one at a time. So they cannot touch the same. Now, with snapshot isolation, then if we have two concurrent transactions, so two clients wanting to do something on the same account, then they are also rejected because they have no, because they have a write conflict if they touch the same account. So this is not allowed under that level. Okay, so then you might ask, I mean, what is the problem? We have these weak isolation levels, so let's just use those. So the problem is that there's no way for us to formally verify a database implementation using these weak levels. So it is indeed the case that there's a lot of literature about these levels. They often fall into one of these two categories. So they could be about these phenomena, which are concise examples of executions, just containing a handful of operations. And these are used to specify these weak isolation levels in the SQL standard. But if you look at one of these phenomena, then this is of course not general enough. We cannot look at this and then reason about all executions between clients and a database implementing one of these levels. On the other hand, we do have some very general models if we look in the database community. But the problem with those is that they work at such a high abstraction level. So they could be using graphs or state transition systems. So this is a graph in one of these models. So it's very hard to look at that and then reason about the individual instructions of a database. So to be precise, there exists no way to formally verify an executable database that runs weak isolation levels. And that's the problem we address in this work. And our tool of choice to solve this problem is separation logic. So as many others, we use the IRIS framework. And in the IRIS framework, usually when we prove a Hoare triple, that implies safety according to some operational semantics. And because IRIS is this framework, we can instantiate it with the semantics of our choice. So our instantiation is called an ARIS. And in an ARIS, we model the network. We model a UDP-based network where messages can be reordered, dropped, and duplicated. So we have tried to at least capture a quite realistic network model. Now, the cool thing about this is that we have a transpiler from a subset of OCaml. So we can write our database implementation in this subset. Then we can transpile it into our logic where it can be verified in IRIS and then recognized in ROC. So that's sort of our stack. So the contributions of this paper is first, separation logic specifications for the most popular weak isolation levels. So these are read uncommitted, read committed, and snapshot isolation. So these are the ones. There are 4 of these levels in the SQL standard, and only 3 of them, these ones, applies to key value stores. So that's what we consider. Then we also have these formal proofs of implication inside the logic, where we show that actually snapshot isolation implies read committed, and read committed implies read uncommitted. And then the last and third contribution is this implementation and verification of a database implementation. So it's just a prototype. It's a very simple in-memory key value store. But it implements snapshot isolation, and then because we have these proofs of implication, then it actually also implements the two other levels. So in the rest of this talk, I'm just going to unfold these contributions and give you a better idea of how they actually work. So for the first bullet, how do we specify these isolation levels? I mean, what do they consist of? So there are two things that we have to do. First, we have to come up with some resource definitions. And these are, of course, not just any definitions. We have to, pick the ones that are going to work and really capture this level. And if you have used a bit of separation logic, you will see that often you have some sort of points to resource. And since we're using key value stores, these will often be, a key pointing to, for instance, an optional value or a list of values. So once you have found the resource definitions that you think are going to work, then you can go ahead and make some specifications for all these database operations. So start, read, write, and commit. So you end up with this bundle of specifications. And do notice that these are not using ordinary Hort triples. These are atomic Hort triples, meaning these operations expose a linearization point. So more technically, then in Iris, we can use invariants to go from the precondition to the postcondition of these operations. And this is very important since we're in this highly concurrent setting with a lot of clients. So these clients are going to want to share resources through these invariants. So let me take you through how it works for snapshot isolation, this one level. So first, we have to come up with the resources. And we have two types of resources. We have like a point to resource for the global database state. So a key points to a list of values, and we call this list a history. So this is tracking all the values that has been written to this key in the past. So for instance, if it's 1, 2, 3, then in the beginning some transaction wrote 1, and then another one 2 and 3, and so on. We also have some points to resources for the local transaction state. So each transaction gets its own resources. So this is going to be a key pointing to an optional value. And then we have this subscript C, which is a connection. So transactions can be started on these connections with the database. And if we just recall a bit how snapshot isolation works, then each transaction has to read from this starting snapshot. So when we are creating these local transactional resources, they have to be created based on the global database state. And if we want the latest snapshot, then we have to take the most recent value out of these histories. So if the history was 1, 2, and 3, then this local resource is going to point to sum of 3. So let's see how this works around the start specification, which is responsible for creating these resources. So again, just to emphasize that starting is about creating starting snapshots. And as you see, there's a lot going on in this start specification, but let's just focus on how these resources are used. So in the precondition, we have the global database state. So this will often reside in an invariant such that many clients can actually create transactions concurrently. And so we provide this in the precondition, and then in the postcondition, you get back the unchanged database state, because starting a transaction doesn't change anything about the global state. And then based on this state, we create some local resources for the transaction which is just about to start. And these are created based on the latest snapshot, so we take the last value out of the history. So with these local resources, now the transaction is ready to do all the reads and writes it wants. And here we have to recall, so to specify read and write, let's recall how that transactions, they run sequentially internally. So you are reading your own writes, and in snapshot isolation for your non-local reads, then you're reading from this starting snapshot that we just created. So this implies that the read and write specifications can be specified just like a sequentially consistent heap. So something that we are quite familiar with. So as you see, the read specification, it immediately reads the value out of the pointer. And the write specification also immediately updates this pointer. We do have an additional resource, which is this key update status resource. And it tracks whether the current transaction actually wrote to this key. So we need this information to track these write conflicts at commit time. So if we just look at the commit specification, and again recall that commit time is all about checking these write conflicts, then I have just highlighted the part which is responsible for checking for these conflicts. So the specification takes a bunch of resources, some of which I have mentioned, and then it uses the pure facts from these resources to express this can commit predicate in red. So this can commit predicate could also have been named like, is there a write conflict? So if you are successful in committing, then this can commit predicate holds, meaning there is no conflict. And in the false case, it means it does not hold. There must be a write conflict with another transaction. So this was like the general idea of how it works for snapshot isolation. And we have also specified things for read committed and read uncommitted using this same methodology. And then we have proven these implications that I mentioned. So snapshot isolation implies read committed, and read committed implies read uncommitted. So I just want to remark about these implications, that it's not just implications between individual Horde triples, it's actually these packages of resources and per operation specifications for all these operations. So in other words, it's these closed formulas on the form that exist some resources such that all the per operation specifications hold. So that is what we're doing these implications between. And having done these implications, we do gain some confidence that our specifications are correct, since if we look in the database literature, in these very detailed models, they specify the same levels and they're also able to prove the same implications. And in addition to this, to gain more confidence in our specifications, we have also verified a bunch of client examples, and these are based on these executions, these phenomena used in the SQL standard. Yes, so the last thing I just want to highlight is this database implementation. So that's like, I think this is the cool thing about our work, is that we have written an implementation, a prototype, in this subset of OCaml, transpiled it into our logic, and then actually verified it with regards to this specification. So the features it has, it's an in-memory key value store. It implements this original algorithm from 95, and it uses something called multi-version concurrency control with timestamps. So just to quickly tell you what that means, so we keep this timestamp counter internally, and then each transaction gets a start timestamp and a commit timestamp. And then if you look at the actual data, then for each key, we have this ordered list of timestamp value pairs. So when a transaction wants to read, we take the starting timestamp, and then we just go down to this list and find the appropriate value. And when you want to commit, we can check for conflicts using the start timestamp again to see if something was written after you actually started. Yes, so just to summarize our contributions, we have these separation logic specifications for these 3 isolation levels. We have formal proofs of implications between them. And then we have a verified database implementation with regards to snapshot isolation, and because of the implications, then it also implements the other ones. So we also have an artifact with this paper where we have our database implemented in OCaml and also all of our proofs in Iris and Rock. Yeah, I think that was it.
Thank you for the great talk. Does snapshot isolation give some sort of guarantee on commits, like at least one of commit succeeds, or is it always the case that you get false or true disjunctions?
So I didn't quite get the last part.
Oh, so like, so the specification for the commit says that you always get disjunction, and so either the commit succeeds or it fails. So I guess the spec itself cannot give you any guarantee on, like, some nodes some clients may eventually succeed or something like that.
No, you cannot get that. I mean, if a client doesn't necessarily eventually succeed, that always depends on all the other concurrent transactions and what they are doing. But if you're only say your transaction is only reading something, then you can never have these conflicts. So then you know that you can always commit. So certain transactions, they actually know that they will commit. Yeah.
Thank you.
Hi, thanks for the talk. You said you cannot use the graph-based models to prove programs, but your colleagues have this Axel logic for weak concurrency, and they use the graph models directly. So I guess why didn't you use it, and could you use it to kind of prove that your models are equivalent to the literature models?
Yeah, so I have actually made some work after I've done this, which does exactly what you mentioned. So we get that any sort of set of transactions that the database produces, from that you can actually prove that it's correct in these more abstract models and in the graph model, for instance. So this is a property we have, yes.
It's cool. Okay. So I guess it concludes your talk, so we should thank you again.